Hello, everybody. So thanks for joining me last time. And today also we will continue working with artificial neuron. And we will try to start programming and try to solve some problems in Colab. Hello, everybody. So thanks. We will just meet for a few minutes until the rest of people join us. I have uploaded, the slides to Blackboard, and also all code are in GitHub. So today we will continue working. Last time we have been talking about the course contents and general terms, which we will go into details. We will go to it into more details later on. So today we will work also with the artificial neuron or a perceptron, because the perceptron is very important. We will try to implement perceptron learning rule, and also we will try to use gradient descent for training our perceptron. So if we will use different activation function. Okay, please just let me know if you can see my screen, and if so today we will talk about perceptron learning rule, adaptive linear unit. So we will talk about adaptive linear unit. Adaptive linear unit, it's a perceptron but with gradient descent algorithm for training or learning. And feature scaling. Last time we have been talking about feature scaling. It's very, very important for learning. Sometimes we can go for the raw data, but it's important to try to visualize your features and try to scale your features. It will help you to improve the learning process, and we will see this today by example, and we will also cover some examples today. So it's a perceptron. We will talk again about a perceptron. It is a basic unit of artificial neuron or artificial neural network. So if we need to build an artificial neural network, we just need to build a mesh of those units and organize it into layers, correct? So this is a feed-forward neural network. So the basic unit of artificial neuron, it is a basic computing unit in artificial in machine learning, or in artificial neural network, it's the neuron or the perceptron. The perceptron, we can use it to classify a task into two classes. It's binary classification problem. So we can use it for binary classification problems. In some cases also, maybe we can use also in some packages, we can try to use multi classes. But in general, we can classify a task into two classes. It could be one positive class and a negative class, for example, or just 1 and 0, for example. So it's according to the type of activation function which we will use. So if we will use hardlim, we can use it for classifying into two classes, one positive class and one negative class. We have a decision line, and this decision line, the value on the decision line equals 0. Above the decision line, it will be classified into positive region, and below it, it will be negative region. So the decision function can be defined as a linear combination of certain input values x and the corresponding weight values omega. So we have omega, we have x. And x, it's the features, correct? So we have some features x, and we selected weight values omega and the bias, correct? Using those omega and the bias, we can create a decision line. We will use this decision line for classification. So this decision line, we will use it to divide my operating region, for example, into one positive region and one negative region. The positive region will be the positive class, and the negative region will be the negative class. So we try to find those combinations. We try to find omega 1, omega 2, omega 3, omega m, and so on. We try to find the bias. Omega values are responsible of rotation of the decision line. So if we need to rotate the decision line, we need to select different values. So if you change the values of omega 1, omega 2, and omega m, for example, we can rotate the decision line. But the bias value, it will cause translation of the decision line. So it can go up and down, correct? So it's a degree of freedom. It's more degree of freedom with us, which we need to keep. So using omega 1, omega 2, and omega m, for example, we can rotate the line, and using the bias value, we can translate the line. We can go up and down on our two-dimensional space, for example. We need to define x. It's the features, so we can define it as a vector in vector space, for example. We call it feature vector, so it could be x1, x2, and xn, omega 1. So the number of omega values will be the same as the number of our features. And we need to use an activation function. The activation function will be if net, it will be equal 1, if net greater than or equal 0, and 0 otherwise. So this is our perceptron. So now we need to train our perceptron. I mean, in the last week, we used this perceptron to classify and or problems, and it was easy to visualize the problem, and it was easy to find a good combinations of omega 1 and omega 2 visually. So we can look into the data set. Okay, we need to put the decision line in that place, and in this case, we need to select the values which will help us to place the decision line in a place where we have two different classes, correct? But now we need to apply a perceptron learning rule, and the perceptron learning rule, it's learning algorithm. Perceptron learning rule, it's a learning algorithm, and this learning algorithm will help us to find a good combinations of weight values and bias automatically. So we just need to work with the data set. I mean, in machine learning, we say that we are working with data or we are playing with data. So we need to extract good values for our weight values and bias from the data. So we need to extract those values automatically from the data using a cost function. The cost function here will be the error. So the cost function which we need to minimize will be the error. We need to minimize the difference between our target values and our predictions. Our target values, we will call it T, right? And our predictions, we will call it Y. And we will do it example by example. So delta omega J equal a learning rate, eta, multiplied by the error, which is T minus Y, multiplied by the input which is connected to this weight value. So I want to change omega J, which is connected to xj. So delta omega J will be learning rate multiplied by error multiplied by this input. Now we need to update the value of omega. So omega J equal omega J plus delta omega J. We will repeat the same for delta B. But B, it's the bias. So the input to the bias, it's +1, right? So delta B will be the learning rate multiplied by the error multiplied by 1. And after that, we can update the value of B. So the value of B will be B equal B plus delta B. So for each training sample, we compute the output value or the predictions. So we apply inputs. We compute the output values, and from this output value, we calculate the error and update the weights using this formula. So perceptron learning rule, it's extremely simple learning algorithm, and it's important to know how to implement it and how to apply it for solving some problems. So this example, I put it in GitHub. If I want to, so this example, you will see it in GitHub. So this is the link. I tried to find a link for it, but it's in GitHub called Perceptron. So maybe it's called Perceptron _PLR. So we will go back to the example. I mean, we need to apply it. We need to apply it for solving one of the problems, and we will apply it for one of the problems, which is the iris dataset. So the iris dataset, in fact, we have 4 inputs. Do you remember? So the iris dataset, we have 4 inputs. We have 4 input features. It's beta length width and the sepal length and width, correct? And we have 3 classes. But as we mentioned, is that a perceptron can be used for classifying only 2 classes. So we will select the first 100 data points, because the 100 data points correspond to the first 2 classes, correct? Correspond to the first 2 classes. The first 50 examples correspond to iris setosa, and the second 50 corresponds to iris versicolor. So we need to use a perceptron. We need to use a perceptron for classifying this problem. So we will start by defining a perceptron as an object, correct? So you can just go to Colab and try to implement this problem. So we need to define a class, an object. We need to define a class as a perceptron, just initialize it with our parameters. We have number of inputs. We need to define the number of inputs. We have 2 inputs or 3 inputs. It's up to you. Number of epochs which we have. So it says a training epochs, correct? So in each epoch, in fact, we use the training data set for, in each epoch, we use the whole training data set, and this is the learning rate. And after that, we need to predict. So prediction, it's simple. So it will be the dot product between the inputs and the weights plus the bias. So in fact, this equation, we calculate net. So net will be omega x plus p. Net equal omega x plus p. And after that, we can apply the activation function. So the activation function, it's binary classification problem, in fact. So the output will be 0 of if, when net is positive, when net is greater than or equal 0, the output will be 1. Otherwise, it will be negative 1. So this is my activation. So in the prediction here, we will provide the inputs. It could be the test data set, for example. And we have the weights already because we got those weights and the bias from the training. So we have the weights and the bias. So we will use this one for calculating net output. So the net output will be dot product of omega multiplied by input x plus bias. It's omega x plus p, omega x plus p. And after that, we will apply the activation function. The activation function, in this case, it will be hard limb function or step function. So sometimes they call it step function or hard limb activation function. So in the hard limb activation functions, output will be 1 when the net input is greater than or equal 0 when it's positive, and it will be negative otherwise. So this is the function for training our model. So we have training inputs, we have training labels, and we will repeat this one for several iterations, correct? So we will repeat this process for for a number of iterations, and in each time we apply it example by example, correct? So we apply the training process, we update weights for each example. It's like stochastic gradient descent. So it's similar to stochastic gradient descent. So for each example, we try to predict the output. Correct? So we initialize first. We initialize weights. We initialize weights here. It's very important to initialize your weights to some random values or some 0, for example. So in this example, I just initialized all weights to 0 values. It could be 0 values, and it could be a small random number. And for calculating the predictions, we will just send this training point. So the training point, we will send it to the prediction function, and using those weights, it will calculate net, and it will apply activation function. So we will see the predicted output. Is it positive? Is it negative? So for each example, for each row of my data, we will send row by row. And for the first row, for example, we will send it to the prediction function, and we will see is it positive? Is it negative? Correct? Is it the positive class or is it the negative class? So we will calculate the predictions, and after that we will update. We will apply those 2 lines for updating the weights and updating the bias. And it's very straightforward. So it's to update the weights, it's the learning rate multiplied by error multiplied by input, and for the bias, it's the learning rate multiplied by error, only error, because the input to the bias is +1. And after that, I will calculate the error. So the error will be, it's the target feature, which is the label minus prediction, and just to keep it for plotting. So I just need to keep it in this training error because I want to plot it later on. Yes, we have some questions.
Yeah, so, hi, good morning.
Yes, good morning, Ron.
Hi, yeah, good morning. Okay.
Mm-hmm. So,
okay, Ravi, you can go ahead.
Yeah, you don't have any questions?
Yes, I do. I want to ask you about, you said you initialize the parameters. Mm-hmm. Can you explain it again? Like, where can we see it in the algorithm? The second question, yeah.
Because I need to in the training process we need to go forward to calculate the predictions, and after that we need to go backward. When we go forward, we need to have our weights. So how can I start at the beginning if I don't have any weights? So it's very important to initialize your weights to some values. It could be 1, it could be 0, it could be some random number. So it's very, very important to initialize your weights at the beginning, because we need to calculate the predictions. And from those predictions, we calculate the error and we will start updating our weights. So it's very, very important to update, to initialize your weights. And strategy for initialization, I mean, there are many ways for initializing it, but it's just to some small random number, for example. It could be from 0 to 1, it could be positive, negative number between -1, -1, for example. It could be 0, it could be 1, right? So it's hyperparameter. I mean, how we initialize also, it could be a hyperparameter. How can we initialize it? So we just need to initialize those weights with any number. And after that, we will go forward, correct? And then when we go forward, we calculate predictions. We will predict. So I will apply one row of data, one line. So I have, for example, for this iris data set, we have 4 features. So we will apply those features, 4 features to my perceptron. So we need to have 4 weight values, correct? So it will be omega multiplied by x. So I need to initialize omega to some random number. It could be a random number, it could be 0, whatever, plus bias. So we need to initialize the weights and the bias. And that is why here I put, I mean, NB.zeros, number of inputs plus 1. Why it's number of inputs plus 1? Because if you have 4 inputs, for example, so I will have 4 weights plus 1 for the bias. So in this case, I will have 5 hyperparameters, training parameters, weights, 4 weights plus 1 bias. So I need to initialize it to some 0 values, to some random values, correct? And I will use this one for calculating the predictions. And when we calculate predictions, we need to calculate error, and we will use the error when we go backward for adjusting the weights.
Thank you, Ibrahim. Thank you.
So your second question?
Yeah, my second question, just like to make sure that I am on the same page. Normally, the net equal MP blah blah is the set activation function, or is it the second part of the function? Just to make sure that I'm using the right wording.
One more time.
What do you call the activation function? Is
activation function? Sometimes they call it activation function. Sometimes there are different types of activation functions, by the way. It could be Gaussian function. It could be sigmoid, right? It could be hyperbolic tangent, correct? There are lots of activation function. But this one, which we have here in this example, they call it hard limb activation function, or they call it step activation function, right? Yeah. So this hard limb activation function, it's just, it converts the inputs into +1 and -1. So all input range will be transferred, or sometimes they call it transfer function. So it transfers inputs from its value into +1 and the -1. Because my problem here, it's a decision problem, right? So I need to classify it into a positive class and a negative class, right? So I need to use an activation function. Otherwise, net here, it will be continuous, it will be float number. So I can, for example, this problem, it's a classification problem. So it's very important to use a step activation function, because I need to decide which class is positive, which class is negative, correct? But in some other problems, like regression problems, in case of regression problems, we need really to keep the output as a float number, because I want to regress. So imagine I want to regress my salary next year, for example, or the temperature tomorrow using historical values. So in this case, I cannot convert it into +1 and the -1, because it would be wrong. No, I want to keep it as it is. I want to keep net as it is. So in this case, I can use linear activation function. And linear activation function, y equal net. So just the output equal input. It will be straight line. So in this problem here, we use step activation function, because it's a binary classification problem. I have 2 classes. So one class, it could be -1, +1, and the other class, it could be negative, or it could be 0, for example. But in case of regression problems, we cannot use this activation function, step activation function, and we need to keep net as it is. So in this case, I need to use, for example, linear activation function. Linear activation function, it's very simple. It's y equal x. Maybe I have some, maybe last slide, I mean, last week we had some. So for example, do you see this is some kind of activation function. So this one, it's hard limb or it's a step activation function. Do you see it?
Yeah.
So we have hard limb transfer function, symmetric hard limb transfer function, linear transfer function. This one is very good illustration. So if it is binary classification problem, maybe I can use this one or I can use this one. But when it's regression, I want to regress. I want to predict the temperature tomorrow, for example. I want to predict stock market price tomorrow for. So in this case, I need to keep the output as it is. So I cannot squash it because those functions is squashing all inputs, all positive inputs here into +1, and all negative inputs into 0 or into -1. So it has this squash impact or squashing effect, correct? But
Yeah.
in case of regression, I don't need to have this in fact, and I need to keep a linear transfer function. I need to keep net. I need to keep the output like linear regression models. So linear regression model, in fact, we did that also last week. So the function is y equal, for example, if I have a single input, it will be mx plus c. So it's a regression problem. So y equal mx plus c. X here, it's dependent variable, and y x is the independent variable, and y it's the dependent variable. So I want to predict the value of y using x. So we try to find m, we try to find the c intercept. So we need to find the slope of the line, and we need to find the intercept with the y-axis, for example. And when we have this equation, we can use it for regression. So the question now, can we do the same using a perceptron? Yes, we should be able to do the same using a perceptron if we will use a linear transfer function. So it's very, very important to try using this linear transfer function. And today, in fact, we have an example. I mean, last week, we had this annual salary data set. So we will use this one also with this adaptive linear unit to predict the annual income using years of experience. So we will use it for regression. So in fact, we can use a perceptron for classification, binary classification, and we can use it for regression as well. In case of classification, you must use one of those activation function. And in case of regression, you must use this function. And also for, you can use also sigmoid, correct? So this one, in fact, it will be this hard limb function or step function. The output will be only 2 classes. It's a +1, for example, and a -1. But if you will use hyperbolic tangent, you will get a number between 0 and 1. And in this case, it will be probability that this input belongs to one of the 2 classes, for example. So we can use hyperbolic, we can use sigmoid, we can use hard limb, we can use symmetric hard limb, for example, transfer functions. So it's according, in fact, to the problem which we are solving, and therefore I just told the people that it's very, very important to invest the time to explore how your data set looks like. We need to get some domain knowledge. So if you are solving a problem for a bank, for example, you need to get one from the domain to explain the data set. You need to visualize it. You need to understand. You need to spend the time, at least 50% of your time. You need to visualize your data, clean your data, pre-process your data, so you can get some understanding of how the data look like. So you can decide which model we need to use, which activation function we need to use. And I guess if you will do this, it will save lots of time later on.
Thanks a lot.
Yes. So we will go back again to our problem. So our problem, it's how we will implement it in Colab. You have the example.
Okay, sir.
Yeah.
Sir, I have a question.
Yes.
So I missed the part where you talked about epochs. What is epochs? Is it the number of times you want to train your perceptron, or is it something else?
So the epochs, it's the number of times for we can call it iterations, for example. So I will train my model for a number of iterations. Those iterations, it could be using block of data, correct? So we can just use the whole data for we go through the whole data set one time and update the weight one time. So we call it an epoch, or we can go through, we can update the weights example by example. So anyway, if my data set consists of 50 data points, so each epoch, in each epoch we will go through the 50 data points time by time. So we call it epoch. So
Okay.
it's iteration or it's epoch, for example, because so I have my data set, for example, in this MNIST data set, we will be working with each time we will go through those 100 data points and we will repeat this process several times. So we call it epoch.
So the higher the epoch number, the better your results will be, is it?
Yes, it should be. It should be. But
Okay.
also,
and choice of 100 and learning rate of 0.01 is your preference, or is there any guideline on?
no, it's by the way, I mean number of epochs and the learning rate, it's hyperparameter, correct? So you need to select. So for example, you will start with some learning rate, and if you see that the performance is not good enough, the accuracy is not good, you can change this number. Maybe you can increase it, you can decrease it a little bit. So in this example, it's constant value, but usually we should work with adaptive value. So we need to start with maybe a big value, and then when we are close to the local minima, we need to decrease this value. So we can go for adaptive learning rate, for example. But in this example, it's constant value. And this learning rate, it's a step which we will use for, I mean, it's a step which we use in the gradient descent, for example. So this is a step which we use for moving across our cost function to reach the global minimum. So if this one is too large, maybe we will oscillate. If it is very small, we will take more number of epochs to reach the local minima. Right?
Okay. But
so the learning rate, it's here in this example, it's constant value, but it could be. I mean, there are many ways we can use for we can go for adaptive learning rate, and in case of adaptive learning rate, it will be a function of the number of iterations. So it could be constant number divided by number of iterations, correct? So when number of iteration is when I equal 1, for example, so it will be this constant value. When I equal 2, it will be half. When I equal 3, it will be 1/3, and so on. So usually, I mean, we prefer to start by big value, constant value, or large value, and we need to decrease this value with time when we are close to the local minima. Because we need to move at the beginning, we need to move with a larger step, and we need to decrease this step when we are very close to the local minimum to avoid, I mean, oscillating across this local minimum. Because we can just keep oscillating across it, and we cannot reach it at all, right? So it's important to start with a large value and decrease this value with the number of epochs or number of iteration. But anyway, the number of epochs and the learning rate, they are hyperparameters. Hyperparameters, which means, I mean, we need to fine-tune those numbers. And the number of epochs also, there is no guarantee that when you increase this number, you will get better performance, correct? Because my performance, maybe it's good in the first 10 epochs, and at 11 and 12, maybe I will start to have overfitting, right? Do you know overfitting? What overfitting mean? So
yes,
so
we need to train your data too much, and then you.
Yes, because I mean, there is no guarantee that when you train your model for 200 epochs or 300 or 400, you will get better performance. Because if I give you a material, if I give you, for example, a book, and I told you to just study this book in a whole semester, and you have the book for the whole time, you will overfit this knowledge, correct? Maybe you will memorize it, so it will be a problem. So I just say, okay, no, I will keep this one with you for a week, and after that you will take your exam. So maybe it's fair, correct? But if I said, no, you'll have the book for 2 months, and after that you will take the exam, maybe during those 2 months you will memorize the book. So I will get bad results also in the exam because you memorized it. But so I mean, it's just an example. So it's like we need to avoid memorizing my data points. So if I let my model to train a lot, maybe at some point it will just memorize my data points, and it will not be able to generalize. So the number of epochs and the learning rate, they are hyperparameters. And we have something called early stopping, right? So in this early stopping, I just stop training at some point, because if we will continue in this way, we will go in overfitting. So we have a technique called early stopping, because I don't want my model to just train forever, because if I will let it train forever, at some point it will memorize my data points, and it will not be able to classify, it will not be able to generalize, it will not be able to predict correct values, because it will memorize my data points. So it will overfit my data points. So we need to be careful. I mean, if we really need to have more number of epochs or less number of epochs. If your model does not have enough number of epochs really for training, maybe we will have underfitting a problem because it didn't have enough time to map inputs into outputs and learn patterns in your data set. And if it's too much, at some point, maybe my model will memorize my data sets and it will not be able to generalize. So we need to be very careful about number of epochs and the learning rate. So the learning rate it's very complex also, because if it is too large, you will go with a larger step at the beginning, but when because you just imagine that the error function, which we try to minimize, it's convex, correct? So when it's convex, we need to move at the beginning by a larger step, and when we are closer to the bottom of the function, we need to move with very, very small steps to guarantee that we will reach the global minimum. So in this case, I need to start with a large learning rate, and when we are close to the bottom of the function, we need to have a smaller learning rate. How can you implement it? As I told you, you can just say, instead of selecting learning rate into constant value, it will be constant value divided by the number of iterations. It's one way for doing it, very, very simple way. But another way also, it could be function of the gradient. Because at the beginning, we have larger gradient, correct? The slope is very rough like this. And when we are close to the bottom, it will be flat. So you can see how much gradient, because I can understand, my model can understand that we are close to the bottom when the gradient is decreasing. I mean, the absolute value of the gradient is small, close to zero. So maybe when it's close to zero, it's an indication that we are very close to a local minimum or a global minimum, for example. So in this case, I need to select the learning rate as a function of my gradient, is the absolute value of the gradient, right? Because it will give me impression if we are where we are in my error function. So selecting the number of epochs, learning rate, it's problems, but I mean by working, by programming, by solving many problems, you will get the knowledge and experience for working with it. So we will go back again to our model. So this is a perceptron. You just need to implement it maybe in this way. And after that, we will go for my data set. I mean, last time we uploaded our data set from Google Drive, for example. But here also we can just use a link. So this is a link from UCI repository, and we can get Iris dataset directly into our program. So we can just have it like this. We need to test the perceptron with the Iris, and this is how the dataset look like. We have 150 examples, and those 150 examples are for 3 classes. And we will use the first 100 values. The first 50 for Iris Setosa, and the next 50 are for Iris versicolor. So we will extract X, we will select 2 features, but you can just do it now. Select, maybe I selected here the first one and the third one, 0 and 2. So this one, it's the first, this one, it's the third. So this one and this one, correct? So it's sepal length and petal length. I used it for classifying this problem. And the target feature Y, it will be the 4th column. So Y will be the 4th column, and I will just replace Iris Setosa by 1 and Iris versicolor by -1. So now I just prepared my data for training. And this code of line here, it's just for initializing. So I will just create a model called the perceptron, and it has 2 inputs. I will use 10 epochs for training it, and the learning rate will be 0.01. And after that, I will just train. So I will train it using X and Y. So X will be the input features, and Y will be the target feature or labels, and I will just train my model. And this is the training error over 10 epochs. So we started by some negative values here, and finally we ended with a 0 error. When it's a 0 error, in fact, it means we have good predictions. That means accuracy is 100%. So maybe we use the 6 epochs for training our model. And this is if we need to plot my data points and just plot your data points and the decision line. So this is my decision line, which we got by using this perceptron. So the green line here, it's the decision line, and we use this decision line to classify or to divide my data set into two different classes. One class, it's Setosa, and the other class, it's versicolor. And we can, of course, calculate the error at the end. The error will be a mean square error. The error function or the cost of value, which we need to accuracy, for example, it could be in terms of the prediction error. The prediction error here, it will be mean square error between target and the predictions. So I just want you to open your Colab and try to implement this problem. You have the example. You have this one. It's called the perceptron underscore BLR. It's in GitHub. So just please download it and start working with it and run it, so we can discuss if you have any questions about that part. So I can share my screen here. I can share my screen and I can run it here also. So okay, so it's okay. I will share my screen with you so we can so okay. So can you see my screen? Can you see my Colab?
Yes, we can see your screen.
Okay. So this is it's called the perceptron. It's in GitHub. It's called the perceptron. I mean, this one, it's just we need to upload those stuff, right? So we just need to run this one. Okay. So this is I mean, implementation of my perceptron. This one, it's just to initialize your object or your class. So it's number of epochs. You can just select. I mean, we can run that part. And after that, I need to load my data points. So I will load my data points from this website. So it's much easier, in fact, than just uploading an CSV file. So this is my data points. You need to spend some time here, in fact. For example, if you look into those features, so those features, its number may be between 0 and 10, for example. So maybe it would be smart to try to normalize or standardize those values. But we will just do it as it is right now. So extract is the first 100 class labels, and I just print y. So it will be like half of it, it's one class plus 1, and the next half it's -1, right? So now our data set is fine. So we will just initialize a perceptron and we will train it using this part of the code. So now we have this output, and those are the weights. So do you see those weights? So print weights. So the weights, in fact, it's omega 0, omega 1, and omega 2. So this is the bias, 0.4. Omega 1, it's 0.7, and omega 2, it's -1.84. So if you want to find the regression model or the equation of the decision line, which is net equal omega 1 x1 plus omega 2 x2 plus bias. So in fact, it will be 0.7 x1 minus 1.84 x2 plus bias. The bias here, it's 0.4. So this is my equation. So the decision line, in fact, the equation of the decision line will be 0.7 x1 minus 1.84 x2 plus 0.4. So those are the weights. So when I try to plot the decision line here, I just did it like this. So I mean, I will get a digital screen maybe next week. So sorry for this, but this is the equation. Do you see? So this is the equation of the decision line. And in that part of the code here, plot the decision line. I just try to find I need to plot that line. So I just, so it will be, it will be in fact, I need to find x1 or x2 because I plot the decision line in two-dimensional space. So if you want to plot your decision line in two-dimensional space, so one will be x1, one will be x2, correct? So it will be like this one. And the equation of the line is, so the equation of the line, it's 0.7 x1 minus 1.84 x2 plus 0.4 equals 0. So this is the equation of the decision line. Do you see it? So this is the equation. I want to plot my decision line. So simply, if I will use x1, if I will assume values for x1, I need to find x2. So in this case, x2 minus 1.84 x2 equal minus 0.7 x1 minus 0.4. I need to find x2. So in this case, x2 will be 0.7 divided by 1.84 x1 minus 0.4. So this is the equation of the decision line, if we need to plot it. Right? So just we need to plot the decision line. I need to find x1 minimum and x1 maximum, and I need to assume some values. I need to generate some values for x1, and after that find the values of x2 using the equation of the decision line and just plot it. So in this case, I will find it, and finally I will run that part, so I will get this output. For the error, if you want to find the error value, prediction error, so it's a 0 in fact. So the accuracy it's 100%. So the accuracy is it's 100% in this case. But remember, in this example, in fact, we didn't test our model. We used the whole data set for training, which is not correct, right? It's just for simplicity. We used the whole data set. We used the whole features. I mean, we have 100 examples. We used the whole 100 examples for training and testing our model, which is not correct, right? So in fact, we need to divide, as we mentioned last time, we have this holdout validation. We need to divide my data set into one set for training and one set for testing. So maybe 8 examples for training and 24 testing. If we really need to get some numbers, which to describe the accuracy of our model. So can you open this file, please, and run it? And if you have any questions, you can just ask me. Yes, Ravi?
Professor, I have a small question. So every point after training the model, when you start testing it, let's say we input a random sepal length and petal length coordinates, and if in case the chance is very less, but in case if it lies on the decision line, what would it classify it as? Would it classify it as class setosa or versicolor?
If what, like, again, Ravi, please? So
everything below the decision line will be classified as class 2, and everything above the decision line is classified as class 1.
Correct.
Right? Yeah. So if in case, in this random case, if in this very rare case where the point lies on the decision line, what would be the output? As in, how would it?
So you mean misclassified, correct?
No. If the point, let's say, if the petal length and sepal length coordinates lie on the decision line, they lie on
so
it.
It will be 0, for example, right? But if we can, I understand you. So if we go back to this activation function, you see here. So in fact, maybe it's a 0, and if it's a 0 or positive values, because it's greater than or equal 0. So if you have a point located on the line, it will be considered this positive class, right? So do you see this equation, Ravi? Do you see this one? So this one,
it will be just assigned to one of the classes.
Yeah, it will be considered as a positive class.
Okay. Got it.
But if you want to avoid this, in fact, so we need to select maybe threshold value, right? So instead of selecting 0 greater than 0, it could be you need to define a threshold value, right?
Okay.
And it will be in this case, this threshold value, it will be just so in this case I can just select this threshold. Threshold, maybe it's equal 0.1, for example, correct? So in this case, we need to select a threshold value, and this threshold value, it will be, it will help us to avoid such cases. So we need to maximize the distance. It will help us to maximize the distance between the data points and the decision line. It's like in support vector machine, because in support vector machine, you know, we have a gap between the closest data points. We call it support vector, and we try to maximize the distance. We need to find a line which maximizes the distance between those closed data points and divide it equally also. So so in this case, maybe if you have this problem, you can use, for example, support vector machine. But in this example here, maybe we need to define a threshold value. Correct? So we can just try and sorry, I need to define it. So I mean, I don't know if it maximizes the distance. Maybe the results is the same also. I mean, I cannot see any. I mean, threshold. I don't know if it has any impact. In fact, having this threshold. So. So I don't know if you can see any difference or not. But anyway, if you need to avoid this problem, you just need to define. We need to define a threshold here. But as I told you, I mean, if you have a data point which is you have a kind of overlap. It's not overlap, but it's a kind of. I mean, and they are close to each other. Maybe you can use a support vector machine. In this case, you will get much better results. But it's in your definition of the activation function, how you will define the activation function. So you will solve this problem if you can define, I mean, this activation function. Okay, so I will just let you work with the code, and we can take, for example, 10 minutes break. During those 10 minutes, you just need to, or 5 minutes, for example, you need to download or just open this file in, it's called Perceptron, and it's in GitHub. So just to try to run this file, and let me know if you have any questions.
Professor, I have a question.
Yes.
Regarding the plotting of decision line, where you have written the function xx2 is equal to minus p.
Yes.
Dot weights. How do we get this function? I'm confused about this.
Yes. Yes. If we have this, but next week we will have this digital whiteboard, so I can write. But I will write the step by step. We have something called net equal omega1 x1 plus omega2 x2 plus bias. I will plot my model here. We have two inputs, x1 and x2. We have two weights, omega1 and omega2, and we have here +1 bias, and we have summation. So net equal this summation. And after that, we will apply this, I mean, activation function. Do you see this one?
Yes, I can see.
Okay, so this one, it's as a decision line, in fact. And this decision line, it's equal 0, correct? This summation equals 0, right?
Yeah.
So if we can find x1, if we can assume values for x1, we should be able to find values for x2.
Right.
Right?
We cannot see, actually, we cannot see the graph very clear.
This one.
Yeah.
Okay.
Take screenshot. Yeah.
Yeah. Sorry, but I mean, next week it will be much better. So sorry for this week. We will get this.
Yeah, I took a screenshot. Thanks.
Okay. So do you see here this equation net equal omega 1 x1 plus omega 2 x2 plus b equal 0. This is the equation of my decision line, and it's the same like the perceptron in the graph. We have two inputs, x1 and x2, and we have biased value. We get summation value. The summation of those weighted inputs or weighted sum, it's a net, which is the decision line. So the equation of this decision line, in fact, it's equal 0. So in this case, if I have x1, we should be able to find x2. So now I will find x2. So omega 2 x2 will be minus omega 1 x1 minus b. Is that correct?
Yeah. So we have to just calculate x2 here, and that's the equation of.
Yes. Okay, right. So just I need to find x2. So it will be minus omega 1 divided by omega 2 x1 minus bias divided by omega 2 multiplied by b. So this is the equation.
Got it. Thank you.
Okay. So this is the equation, but I mean, in fact, this is very easy way for doing it, and it's simple. But maybe in complex situations, so if you have a feed-forward neural network, you need to generate a grid of points, and you need to substitute those numbers into the prediction function to get much fancy plot. So this plot, it's very, very simple. Maybe it's okay for today, but maybe next week we will try to make more fancy decision line plot, because this one is very, very simple one. If it will be more complex, maybe it will be harder to do it like this one. So another way is to generate a grid of points between x1 and x2 and send all those points to the prediction function, and it will just classify each point into plus negative. So we can plot, we can have a better graph, in fact, for the decision line. So here it's just a line, but if you can generate a grid between those values here and those values here, and send all those data points to the function which is called the predict, you can divide this graph, all those graphs, into negative areas and the positive areas, and you can plot it into different colors. So you can do it in a much better way. So in fact, I don't recommend you to do it like this one. I recommend you to do it by the prediction function using this one, predict. Where is predict? So we have train. Where is predict? So in fact also maybe it's not smart to do. Okay, I just try to find coordination. I mean coordinates of each point and plot it like this one. But we have this function here. You need to use it. Train. Okay. So in fact, you should use this function, predict. Correct. So in fact, I can create a grid of points. You know this is the inputs. So I can plot the decision line using this function, in fact, because I have inputs, and I know those inputs, it's x1 and x2. So just need to generate a grid of x1 and x2 and send it to this function, and the output will be the decision. It will be plus negative. Using those plus negative, you can plot the decision line. I will make it and I will share it with you, or I can. But for this week, I just said maybe it's much easy to make it like this one this week. But next week we will make fancy decision line plot. We can create a function for doing it. Yes. So did you all run the program from GitHub?
Yeah.
Okay. Yes, Rasmus, we have this whiteboard function in Zoom, but I try to use my mouse to plot by it, but it's hard, in fact. Yeah, it's yeah. Okay. Yes, it's hard, but we bought Wacom, in fact, and we will get this Wacom maybe today or tomorrow. The plan was to get it last Friday, but they ordered it late. So we will have better tool, in fact, from next week. So where I can just write by my hand. So it will be much better than using a mouse. So next week we will fix it for sure. So if you are done with this example, I can ask you to Okay, so we have some notes here. The perceptron learned a decision boundary that can classify its iris training subset perfectly. BLR converge if and only if the two classes can be separated perfectly by a linear hyperplane. So it's very, very important that PLR is working very fine with linearly separate a linear decision boundary. The weights will never stop updating unless we set a maximum number of epochs. So in fact, we have a problem. If your problem, if we cannot find a good decision line, it will keep training forever. It will not converge. So we need to define maximum number of epochs. So when it reaches this number, it will just stop by itself. Okay. So can I ask you if in this code, in fact, can I ask you to normalize? So here, do you see here in this graph? I mean, we are working, I mean, numbers between maybe 0 and something, and these numbers, it's large numbers. So can you normalize those numbers? Can you standardize those numbers? We have an equation from last week, and it was, so if I have x, for example, and I want to standardize it, I need to subtract x minus x mean, correct? X minus mu divided by standard deviation. So can you implement this one, please? You just need to add one line here and test it. So just in this perceptron code, I mean, save it, for example, in your drive, and just try to modify it. I mean, here, before training, here, I mean, before plotting the decision line, before training, we need to do some pre-processing here, right? Here, I mean, we need to add something here, because here we use we just use the x, but in fact, we can use x normalized or x standardized, for example. So we need to find x standardized. We need to add one line here. If you can see my screen, we need to standardize the data set. Feature input, feature vector, for example, we need to standardize it. So we need to implement it. It will be, we need to get something x minus mean, right? X minus x mean, for example, we need to do something like this one, x minus x mean divided by standard deviation. Standard deviation sigma, it's x minus mu divided by sigma. So please, can you do it? We need to add one line here to standardize our data set. So I can give you, we can take 5 minutes break. So I want you, please, standardize your feature and retrain your model and the plot. So we just need to add one line here. We need to add one line here. So we will stop now for maybe 5 minutes break or 10 minutes, for example. Just maybe 5 minutes is enough. And after that, we can start again. And after the break, I mean, please show me how you will standardize your data set. So the equation is simple. It's x minus mu divided by standard deviation. So, I mean, this is, so did you make it? So no, in fact, we can just use x and n. We can use x and y as it is, or we can use this equation for standardizing the feature vector using this line here. It will make life much easier for the learning algorithm. And BLR here, it will converge faster, in fact, when we standardized feature inputs. I mean, last time it takes maybe 10 epoch to, to learn my data set. Now it takes maybe just one by chance or two, for example. So it's really much easier. So we use only two features to make it easy for visualizing. Okay, we just got So can you open your mic, please? Can you open your mic and you just, is it okay? Is it working with you? I just repeat it one more time and I got this decision line, but of course I need to modify, the learning rate. So I need to increase the learning rate a little bit. And when the data was normalized or standardized, in fact, my model can converge much faster, as you can see here. And this is a decision line, and maybe it's it looks better and it looks okay when the data was normalized. Standardized, sorry, the data was standardized. Okay, so we can go back to the slides and
So actually, I want to ask one thing, that when in standardization of the inputs X, when we change the axis of in the mean function or standardization function, standard deviation function, we get different results. What does that mean? That when we put x is equal to 0, it gets a different, x is equal to 1 gives us completely different results. And
okay, because you have two columns, right? You have two columns. X, it's two columns. So, and if you didn't put x is equal 0, you will get one average value for all data points as a one column, right? So you will get a single value.
All right.
But if you put x is equal 0, you will calculate the mean value across rows. They call it across rows or across column. Across rows, across column. Yes, it will be across column. So if you didn't, so I can show it to you. I can just share my screen with you. And so do you see my screen now? So I will just remove that part, right? No, I will just put it here. So for example, print np dot mean of x. We will run that part. So you got 4.16. Do you see this number?
Yes.
And if you changed it, if you added that part here, x is equal 0. Do it one more time. So now you got two values. So it's the mean value of x1 and the mean value of x2.
All right. Got it. Thank
Yes.
you.
Yeah. So it's very important to be sure that you are getting, and it's the same also for standard deviation. So I can just make it like this. Okay. So now now we are all in the same page, right? So I will share my slides one more time. Okay. Okay. So I mean the last perceptron we used it for classification. I mean last week we have been working with this annual income in terms of years of experience, and it's regression problem, right? I mean Rasmus last time he made the code very quickly and he made a regression model for it. We need to do the same but using a neuron or a perceptron. We will not call it a perceptron. We will call it adaptive linear neuron, because it's a regression problem. So in this case, we cannot use this kind of activation function, and we need to use other type of, if it is regression, we cannot use this hard limb symmetric or hard limb transfer function. We cannot use those. We cannot use this one. We cannot use sigmoid, because the sigmoid's output will be number between 0 and 1. And now we want to regress income. And in our data set, the income maybe was big number. Maybe it was from maybe 0 until 5-6 millions. I don't remember. So we cannot use this one for regression. We cannot use this one for regression. We must use a linear function. So we will use this pure lim function or linear transfer function. And this linear transfer function, it's just y equal input, y equal x. So for this hard limb function, in fact, y equal +1 when n is greater than or equal 0, and -1 otherwise, or 0 otherwise. So this one, it's a step function. It's a very simple one. But for regression, we can't use this one. We must use a linear function. So in this case, we will try to, it's like a perceptron, but instead of using a hard limb function or a step function, we will use pure limb function or linear function. And in this case, we will try to minimize, we will have a new cost function. I mean, last time the cost function was just t minus y. Do you remember? So with a perceptron, the cost function which we try to minimize, it's t minus y, right? No, here we will change it. It's similar to error backpropagation. It's a gradient descent. We will use gradient descent to adjust the weights. So we will use this cost function. So the cost function will be half multiplied by summation of target minus predictions square. Why it's half? Because we will differentiate this one, and it will be 2 times half, it will be 1. So we don't care about this half. It's just constant multiplied by our cost function. So it doesn't matter for us. We just make it half, because when it's half, it will make life much easier later on when we differentiate. So we put it half here, because when we differentiate, we will multiply 2 times half, it will be 1. So it's mainly, it's just the summation of squared error, So we will use PLR in case of perceptron learning rules. Weights are updated based on a unit step function. We use this unit step function. But adaptive linear unit introduces the concept of minimizing a continuous cost function. We have a continuous cost function, and it's convex because it's squared here, so it will be convex. So in this case, we will be sure that we will reach a minimum value. It could be global, it could be local, right? there is no guarantee also that it will be local or global minimum, but anyway, we will reach a minimum value. This cost function will be the sum of squared errors between the calculated outcome and the true class label. So it's the difference between target and output. There are many different types of activation function: sigmoid, hyperbolic tangent. Those are the modern nonlinear activation function, like rectified linear unit, leaky rectified linear unit, exponential linear unit. So those activation functions, we use those activation functions, in fact, in deep learning. So those activation functions are very, very important. We use those activation functions in deep learning. And today we will know the difference. Why? Why should we use ReLU instead of using sigmoid, for example, or hyperbolic tangent? Or so anyway, for our problem today, we need to implement a perceptron for the data set which we used the last time. It's this annual income, and using adaptive linear unit. So this is the function, or this is the, so we have some inputs. We have x1, x2, xn, for example, and each input is associated with a weight value. Remember, we have a bias here. I forgot to put it here. So we have a bias. Bias is very important. Don't forget the bias, but you can consider the bias as an input, right? So I can just add one more input here, and the input will be +1, and the weight will be the bias value. So in fact, it could be okay. We will calculate the net input. So the net input will be just multiplications of omega x. So omega 1 x1 plus omega 2 x2 plus omega n xn. And after that, we will apply it to the linear activation function. Linear activation function, it will do nothing. It means y equal input, y equal x. So it's a straight line with a slope of 45 degrees. So y equal x. Here we have our output here, right? So this one will be the prediction. So we will use those predictions with the target values to calculate the error, and use those for adjusting the weights using a gradient descent. So the cost function will be half multiplied by t minus y squared. And we need to update the weights. So to update the weights, omega equal omega plus delta omega. We need to find the delta omega. If you will use gradient descent, so the formula will be minus eta multiplied by partial j by partial omega. So it's minus learning rate multiplied by the gradient. Why it's negative? Because we need to move against the gradient, right? And I will explain it here. Why it's minimum? It's because in perceptron learning rule, we just used this equation. In fact, it was learning rate multiplied by error directly, by target minus y, t minus y. But here it's minus eta minus learning rate multiplied by the gradient. So the gradient will be the first derivative of the cost function, partial j by partial omega. So partial j by partial omega, in fact, we can find it using the chain rule. Partial j by partial omega, it's partial j by partial y multiplied by partial y by partial omega. Because there is no connection, in fact, between j and omega. Can you see anything here? We cannot see anything because the target is not function of omega, but the output is target of omega, is function of omega. Because y equal the summation, y equal net, and net omega equal omega x. So in fact, this output here, it's function of omega, which means when we change omega, we can change y, right? So delta omega will be minus eta multiplied by partial j by partial y multiplied by partial y by partial omega. We call it chain rule because I want to find partial j by partial omega. So this is partial j by partial omega. In the middle here, we have by partial y, partial y. Right? So partial j by partial y, it's a 2 times half. 2 times half. So 2 times half. So the half here disappeared. And multiplied by the first derivative of t, which is 0. First derivative of minus y, it's negative. So we have negative sign here. Now we have partial y by partial omega. Y equal omega x, correct? Y equal omega x. So partial y by partial omega, in fact, it's omega. Sorry, partial y by, partial y by partial omega, it's just x, the input. And this one, it's squared. the cost function is squared, so it will have this convex shape. It will be like this one. We need to minimize it, which means we need to find combination of omega, which will minimize J. We need to find the J minimum here. So we need to find this value here, in fact. We will reach it anyway. When it's convex, we will reach this global minimum. And how can we work here? We just initialize the weights with some values, random values. Those random values, maybe it will place us here, maybe it will place us here. If we are lucky, it will place us here. So imagine that we are here. We will calculate the gradient here. So the gradient here, in fact, it's okay. We have some questions. Okay, Masoud, thank you very much. So I will share the recording with you later on. So after 12, we will have recording. So I will share it in Blackboard. Thank you very much, Masoud, for joining me today. So we have this graph. I mean, how this one will work, we will initialize the weights with random values. Random values means, I mean, using some random values, maybe we will be here, maybe we will be here, correct, somewhere. If we are here, for example, we will calculate the gradient here. And if you can see the gradient here, it's the slope of the line, in fact. So here, the slope, it's negative. Here, it's positive, correct? So when it's positive, which means we need to move in that direction, but we multiplied it by negative. When we multiply it by negative, it means we will move against the direction of the gradient. So because this direction, in fact, it's the positive direction, which means this is the direction of increasing omega. So in this case, now we will move against it. So we will move in the direction which will decrease the value of omega. So this omega, it's located here. So in this case, we will move against the gradient because this one multiplied by negative. So we step by step, we will reach this global minimum, right? We will find this global minimum. We will reach it here. Imagine we started here. So when we are here, for example, imagine that we selected some initial weights, and those initial weights placed us in that place, right? So in this case, in fact, logically, we need to move in the direction of increasing omega. How can we do this? We will calculate the gradient. So partial J by partial omega here, it will be the slope of the line here, and this one will be negative. When it's a negative, negative multiplied by negative, it will be positive. So in this case, delta omega will be positive. So in this case, we will move in the direction of increasing the value of omega. So we will move forward. But when we are here, the slope here will be negative. The slope here will be positive. So positive multiplied by negative, so this delta omega will be negative. So when you update your weights, you will move in the direction of decreasing omega. We will move in that direction. So anyway, when we apply this algorithm for some iterations, we will try to reach the global minimum here. So there are two ways also here, by the way. So we can, in the notes here, instead of updating the weights after each individual training sample, as in the perceptron, we calculate the gradient based on the whole training data set. We can do it because we have a summation here. Do you see the summation? So we can keep the summation with us, and it will be the summation over, we calculate the gradient over the whole data set. So we call it, batch training or batch learning, for example, batch gradient descent, or it could be example by example, which is called stochastic gradient descent. So it's just, this is the training mode. It could be batch gradient, it could be mini batch gradient, and it could be stochastic gradient descent. So in case of batch gradient, we will calculate the gradient over the whole data set in each epoch, and we will use maybe the mean value of the gradient for updating the weights. So in fact, we will calculate the gradient for all my data points, and we will use the average gradient for updating the weights. So in fact, we will update in batch gradient, we update the weights one time each epoch. So we update the weights one time in each epoch. But in stochastic gradient descent, they call it online learning. So when we have a new data points coming in, we will calculate the gradient for these data points, and we will update the weights for these data points. And it's more suitable for online learning. And it's suitable when we don't have too much memory, in fact. We don't need to store values and store all data points in our system because we don't need it anymore. We will just use one point. We will use it for updating the weights, and just ignore it. They call it online learning. So the formula, it will be omega equal omega negative learning rate multiplied by the gradient. And if the step is too small, if the learning rate is too small, so the gradient descent can be very slow, correct? And when it's too large, so the gradient descent can overshoot the minimum, and it may fail to converge or even diverge. So I got this question today about the learning rate. So the learning rate, in fact, it's the step, it's eta value. So if this value is very small, what will happen? It will take many number of epochs to reach the minimum value, the global minimum. And if it's too large, what will happen? We will just oscillate across the minimum value. So we will just keep oscillating. Maybe we will fail to converge, or even we diverge, right? So in this case, we need to select a smaller value. And we can do it, in fact, in the last example. So if I can share it with you, I will just show you how can we diverge. So, so we will go to this collab, the perceptron, and I will just increase this value, for example, to 4.5. And we will run it. No, it's still fine because I normalized, in fact. We have a problem here because I normalized. If you don't to normalize, it will diverge, in fact. No, it's fine. No, I mean, there is no hope. But if you can go to the old version of this example using just X and just increase this one little bit. When you increase this one little bit, it will diverge. No, we still have very good results here. So it's, in fact, when the data point, it's not standardized, your model is very sensitive to the learning rate. So when you increase this one, very small value, maybe it will just diverge. Okay, so so now we will go for implementation. We need to implement this adaptive linear unit, and we need to use it for, maybe it could be also for maybe for iris dataset, right? And if you want to use it for iris dataset, you need to add that part here. We need to add the threshold function because I need to have two classes, right? So you will get some values here, but you need to define a threshold function here. So when the value here it's greater than or equal some threshold values, output will be 1. Otherwise, it will be -1. So we need to add this threshold function if you will use it for classification. But if you want to use it for regression, just ignore that part. Ignore the threshold function and use the output directly. So if you want to use it for the salary data set, which we used last week, you don't need to have the threshold function here, because we just need to get the regressions as it is. We need to get those numbers directly here. So in fact, this adaptive linear unit, adaptive linear neuron, we need to use it 2 times. First time with iris dataset, and second time we need to use it with, to predict the annual salary in terms of the number of years of experience. So please, you have also the code in GitHub. So I mean, for it's the same. In fact, it's the same. So so we have this adaptive linear neuron. I just uploaded my data points and I extracted X and Y. Right? We did that last time. This is the same, and this is the function which we implemented. I just need to make some small changes here, in fact. So the weights, I will update, I will initialize the weights to random values. I mean, last time we initialized the weights to some 0 values, but this time it will be random values. And for the number of epochs, we will calculate X multiplied by omega. So we will calculate net. And after that, we will apply this linear activation function. And when you have this linear activation function, I will calculate the error, because we need to calculate the error here for updating our weights. And after that, I will update my weights. So it will be, I mean, delta omega, it's eta. Delta omega, it's eta multiplied by summation of error. I just use the mean value of the mean value of the gradient. In fact, the gradient will be it will be the error multiplied by x, correct? So delta omega, it will be the summation of target minus y, summation of t minus y multiplied by x, right? So the error here it's t minus y multiplied, but because this one it's a summation, we have summation in fact, but this one it's a vector multiplication, so it's the same. So you have the error values. This one it's a vector, right? This one it's a vector. It's t minus y, target minus y. So this is the vector multiplied by x. So this one will be summation. It will be scalar value. It will be a vector, and I will get the mean of it. In fact, so this one it's the minimum mean gradient. So I will do the same also for the bias, and after that I will calculate the cost function. So the cost function it will be half multiplied by error squared, the summation of error squared. And the prediction, I mean the prediction, you just need to define a threshold. I selected threshold here equal 0. So when net is greater than 0, the output will be 1, otherwise it will be -1. And just try to implement it and plot the training error. So we need to see the progress. So we started at very high error value, and after 10 epochs we reached very small error value, right? And of course after that we will plot the same as we did last time. We will plot the decision line. So you will just do the same. You will just do the same. Here, for example, it's the learning rate. What is the impact of the learning rate? So this learning rate, it's this one. It's very small. It's 0.001. So it converge. In fact, correct. It converge after 20 epoch. But this one, when I increase it a little bit, what happened? It diverge. So the error diverge, which is a problem. So selecting. So the error, in fact, the error rate, in fact, or the learning rate, in fact, it's hyperparameter which we need to select carefully. But you know, this one it's very sensitive because we didn't use standardization, in fact. So when your model has a problem, you really need to standardize your data, spend some time with your data, because it will save lots of time later on. So please, now we will go back to this code, and I wish if you can just go to the GitHub file, try to download it, and run this code. So we can have 10 minutes and discuss the code after 10 minutes. And I will share it. It's called adaptive linear unit. So I will open it here in my computer, adaptive linear unit. Yeah. Okay. So we have the code here. Yes. So it's the same problem, but instead of working with a perceptron, we used adaptive linear neuron. Adaptive linear neuron, it's different cost function. Different activation function. We will use linear activation function. And instead of working with PLR, we will not be able to use PLR here, because PLR it's meant for binary classification problems. Here we need to use gradient descent. Gradient descent, we need to define a cost function. The cost function must be convex cost function. So it will be half summation of t minus y squared. Yes, so it will be the same, just you can just copy the one for a perceptron and just try to modify that part. So we will take 10 minutes. We can take 10 minutes. After 10 minutes, we can discuss your code. Yes, Ahmed, please. Amin, do you have any question?
Yeah. Yes, and then I just want to make sure that I understood it correctly. So the input function is the one that you are referring to as the cost function in this algorithm.
Yes, as a cost function for this algorithm.
Is the input function, okay. And then the linear activation function is, of course, the activation function. And finally, we have the threshold function, which is the last part of the coding, which is the net bigger than 0. Okay, so
we use
correct wording.
Yes, we use, in fact, I will share my screen.
Yeah.
We use, so just ignore this threshold function. So if you want, because we had last week a data set called, it's a salary data set. And this salary data set, we try to predict the annual income in terms of years of experience. So it's just a pure regression problem. And in this regression problem, we can solve it using, so y equal mx plus c. Y will be the annual income, and x will be, it's the years of experience. And m, it's the slope of the line, and c, it's the intercept with the y-axis. So in fact, we can find a regression line. But if you want to use this problem for classification, how can we use it for classification? If you want to use it for classification, we need to add this threshold function. So this threshold function, it will convert this continuous output into two values, maybe +1 and -1.
No, I have followed the last recording. I have actually
Yes.
went through it, and I also went through the years of experience problem. So
Okay.
I'm kind of familiar with it. So for regression, we avoid it.
So in regression, we avoid it. But if you want to use it for classification, we need to, because in classification, I need to make decisions, yes and no, black and white. So in this case, we need to use this hard limb function here. Or threshold function. Don't call it an activation function. We just call it threshold function, for example. So if we can go to the code, I just, I mean, we will use here, I mean, in this for loop, for example, do you see this for loop? So the training will be done here. So the training will be done for each epoch. So we will calculate the net value. So the net value will be the dot product of x and omega plus b. So this one, in fact, it's net equal omega x plus b. Y equal net, because it's linear activation function. So linear activation function, it's nothing will happen here. Just the output will equal to the input. Y equal net. We don't have any, it's a linear activation function. So this one, it's linear activation function, which is, it was like this one, y equal x, for example. So, but I will just remove it. Anyway, y equal x, whatever. So the error will be t minus y, correct? And now we need to update the weights. So how can we update the weights? So in fact, we need to go to the, you don't see my code. I can just use my screen, yes. Can you see both my, so please, can you see my slides and my code?
Yes, we can see both of your screens.
Okay. So do you see? We have here this is y equal net. In fact, it's that part, right? It's a linear activation function. So first, we need to calculate net. Net input or net will be omega x, just omega x plus b. So this is net equal omega x plus b. And after that, we will apply this linear activation function. So y equal net. Now I want to calculate the error here. So the error here will be t minus y, target minus predictions. I want to update the weights. So delta omega, do you see delta omega? Omega equal, in fact, it's equal minus learning rate multiplied by the gradient. But when we find this first derivative of the cost function, it will be this one. It will be learning rate multiplied by summation of error multiplied by x. So it will be learning rate multiplied by summation of error multiplied by x, right? So this one, it's a summation of t minus 1 multiplied by x.
Professor, can you explain why haven't we used the negative sign with this?
Here?
Yeah.
Okay, because when we differentiated this one, when we differentiated partial j by partial y times partial y, can we find partial j by partial y? This one?
Yes.
It will be 2 times half, right?
Yeah.
So what will be remaining? It's t minus y. But we need to differentiate what is inside. So the differentiation of t, it's 0. The differentiation of y for y, it will be minus 1. So this one will be negative t minus y. So it will be negative summation of t minus 1, right?
Right.
And the partial y by partial omega, y equal net, right? Y equal omega x. So partial y by partial omega, it will be just x. We have here negative times the negative, it will be plus.
Thank you very much.
So now this one will be plus. It will be here plus and it will be here plus. So I'm taking the mean. Some people, they don't take the mean, just summation. I mean the summation of, so you can try to remove this mean value and test, but I just used the main gradient for the main gradient in the epoch, in fact. So here, do you see in this epoch, in each epoch, we calculate net for all inputs, we calculate y for all inputs, we calculate the error, so this one will be vector, and after that I will update the weights only one time in each epoch. So in fact, it's we call it batch. I mean batch gradient descent, right? It's batch gradient descent because we update only one time in each epoch. We update only one time in each epoch. So now we can run it. So I will just run that part. Now we will run this data. We uploaded it. That part is okay. We did that last time. We will do here. After that, we will go here for. Now we have. Do you see? So we started from large values. I mean here in that part, in fact, we just initialize our model. Learning rate is very, very small value. And we train our model using X and Y. We calculate predictions. Those are the predictions. No, this is the error, in fact. This is the error. So this is the cost. It's the error in each epoch, right? We have 10 epoch. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those are the weights, model weights, omega 1, omega 2, and bias, right? Or sorry, this is bias, omega 1, and omega 2. And those are the classes. Predictions, all predictions are negative. We have some problem here, I guess. Okay, we need to test it here. No, we have a problem here, in fact. We have some problems, right? So maybe we need to increase this one a little bit. Train one more time. This time it's all positive and it's a diverge. Do you see? And instead of converging, it's a diverge now. So as I told you, when you use the data points as it is, it becomes very sensitive, in fact. So we try one more time. No, we have some problems here. No, it misclassify all. So the accuracy now it's 50%, correct? Okay, I will ask you, what is the accuracy here? We have 50 data points Setosa and 50 data points versicolor. What will be the accuracy here? Can you estimate the accuracy of this model, please?
50%.
How much?
50%.
Yes, correct, 50%. So the ground truth, in fact, it's 50%. So the ground truth, it's 50%. So the accuracy now, it's 50%. But we have lots of problems here, in fact. We have lots of problems. I don't know why it's not. We can check the code. Maybe we can try to fine tune the learning rate. Now it's much better. Do you see? So I guess the accuracy now will be okay. We need to plot this one more time. Now we are okay. So it's very, very important to fine tune your learning rate. Right? If you increase this one little bit, we will see what will happen. Now its accuracy is, again, it's 50%, right? So we need to go back to this. So it's a very sensitive, in fact, to small changes in the, now it's a problem again. Okay. No, it's fine because I mean we need to. I mean because we initialize it each time from different. We need to fix this one to select the same random values. In fact, maybe. So we need to. Do you know how to do it? So we need to select a seed for the random generation. But as I told you, it's a problem, and it's important to try to standardize your data set. So here in that part, in fact, I will visualize the distribution of my feature inputs. So I calculated the mean value, standard deviation, and I will try to plot it here. So in fact, we have two features, right? So this is the first feature. This is the second feature. X normalized. 0, okay, so this is the first feature, and it's standardized form. This one. This is the second feature, and this one it's standardized form. Now the mean value it's 0, and the standard deviation is 1. Right? So this is the original one. This is the raw data, raw feature. It's petal length and sepal length and petal length, and then when we standardized it, it will be like this one. When it's standardized, in fact, we should get much better performance. So now we are testing. So it's more smooth. I will talk about it why this one looks smooth. But the performance and the learning rate here, it's much higher. It's 0.1. And if it's 0.2, it will not converge. It will not diverge. No, it diverge, unfortunately. So maybe this one should be something like this one. Okay, so it converges much faster, in fact. Do you see? So we don't need 20 epoch, in fact. Maybe just 5 is enough when the data is standardized. Do you see? So it's much, I mean, the performance will be much better. So did you run this code? Do you have any question for this example? Do you have any question for this one? Can now you just repeat this one for the salary data set? Now we use this one for classification. Can use it for can you try to use it for regression? So how to improve the gradient? In fact, gradient descent using feature scaling. So we use standardization, which will shift the mean and the variance of each feature so that it's centered at 0 and has a feature standard deviation of 1. So we will just apply this formula. So when we apply this formula, we will standardize all our feature space. So the feature space will be standardized. It will take mean of 0 and the standard deviation of 1, which will improve the performance of the gradient descent. So when we train it using scaled features, we will get such kind of performance. Okay, so now we need to solve this problem. It's from last week. Can you see my slides? Okay. Okay, great. So please, just we need now to I mean last time, Rasmus, he built regression model, and those numbers I got it from his code last time. So when it's regression problem, y equal omega x plus b or mx plus c, right? So when it's a neuron, we just call it y equal omega x plus b. When it's a regression model, I mean it was mx plus c, in fact. So those are the parameters of the regression model. Those are the parameters of the regression model. So this one will be the slope of the line. This one will be this. So in this graph here, this is the result of the regression model. When it's a regression model, we have X and Y. Y, it's the annual income, and X, it's in years of experience. And now we have a straight line. So we can use this straight line to regress the income in terms of years of experience, right? So we got this one using a regression model. So can we do the same using adaptive linear unit? So just please, I mean, try to modify this code or modify the one which we used the last time to try to predict, try to find, we need to find this one. I mean, this is my results, which I got. So we need to use adaptive linear unit for regression. In this case, it will look like this one. We will have only one input because here we have only one feature. So the equation should be y equal omega x plus b. We need to find omega and b. So a result equal or similar to this one. I didn't make any comparison in terms of accuracy and stuff like this between the regression model and adaptive linear unit, but it's just for us, we just need to know how to implement it. So now just modify your code. I mean, you have the code already, this adaptive linear unit regression salary dataset, but I don't recommend you to go to it directly, but try to modify this one, for example. Try to modify this one. It will be more simpler because we have only one input. I mean, in this example, we have two inputs. Here we will have only one input. And of course, here we don't need to use, I mean, in the prediction here, we don't need to use that part. So predict here, we will just predict net. We will return here net, not this one, because this one it's a threshold function, right? No, this we just, so in this case we just need to play with net directly. We don't need to have this threshold function. So please try to modify it. We will take 10 minutes, and we will meet after 10 minutes. But I need someone to present. I mean, to present his solution. So just please, take your time and try to modify this one into a regression problem. Try to modify this one into a regression problem. We used this one for, we used here batch gradient. Of course, we used here batch gradient descent. And we used this one for iris data set and for classification. Now we need to change this one into this problem. We need to use it for a regression problem, not a classification problem. So so we will stop, and we will meet after 10 minutes for discussing your solution, how you will do it. So please try to share your screen with the rest of us and try to, describe your code and discuss. We need to have a discussion in the classroom, even if we are in remote places. But I guess I allowed all people to try to share their screens. So you are free to share your screen with the rest and discuss your code. Yes, Amin, do you have any question?
No.
Okay. So, but please, if you are working in a code, or if anyone want to share his screen, he can share his screen with all of us, and we can discuss his, code for this annual salary regression problem. So I need to open it. Maybe it's this one. I tried to search for the code. So it's called. So in my screen now, we have the code for this regression problem. So in the first part here, we need to, I will just leave you. Should we have more time to for you to just try to solve it? Okay, 5 minutes. We will have more 5 minutes, so we can discuss. But don't open this file, please, and try to make your own file, or we need to discuss. And if you want, you can just run this one and discuss. So we will discuss again after 5 minutes. So now it's 10:23, so it will be 10:28, for example. We can discuss your solution. Now it's 10:28. So do you like to share your solution or something? Anyone want to share his screen, or I can just talk about the code? So, I mean, as usual, we just upload all those libraries. And this is my data set. So now it's file. We will use this files.upload. We will get it. So now we have our data set. Just plotting it to see what is going on. So this is our data set. We can plot X with Y. So X will be the first column, Y will be the second column. The first column, it's years of experience, and the second column, it's annual salary. Imagine it's a KNOC, 1,000 NOK. So this is our function. It's the same, exactly the same as the one which we just did for classification problem for iris. I mean, there's no difference. It's just the same, but instead of using, as I mentioned last time, in predict here, we need to make some changes. So now we will return a net. We don't need to have this. We don't need to have here the I mean threshold function. We don't need. So I can just write a note here. No need for threshold function. In regression. We don't need this threshold function here because we will regress. So we just need to use net as it is, right? So here we will use net as it is because we need to find the line. We don't want, in fact, we are not interested in classifying something into two regions, for example, positive area and negative area. No, we are just interested in this line because we will use this line for regression. We will run that part. Scaling features, as I told you, it's important. So when you, I mean, we need to have this pipeline for machine learning. So we need, when we are getting our data, after collecting our data, we need to visualize our data. We need to do some pre-processing. One of the most pre-processing step in our data set, it will be standardization of our feature set, for example. So we will do some feature scaling. We call it feature scaling or standardization feature. Okay, so we will do it, and after that we will create a model, and we will train our model using standardized data set, and we will predict, and we will plot. So we will just run that part. So here we have it's the cost, it's the error, I mean the cost value, I mean the last error value or something. Maybe it's not important, but this is the model parameters. We have those model parameters. We have only two, right? So for the model parameters, we have only two. We have omega and we have bias. So we have here two values, right? I mean, the first value, it's omega, and the second value, it's the bias. Maybe not, maybe it's a mistake, in fact, because here, omega 0, it's the bias, and omega 1, it's the weight. So in fact, I'm mixing them here. So in fact, we need to copy this one. We need to change this one, because this one, it's not the bias. This one, it's omega. And this one, it's the bias, right? It's according to the order which we use in the code. So now it's my model, and this is the training error for epochs. It takes maybe 125 epoch to converge, right? So I will just do it one more time. So it takes maybe around 125, 150. And you can continue. I mean, if you want to decrease this error, you can just continue for longer time. And you can also adjust this learning rate. So if we will see if we put it for 0.04, so maybe it's much better. Do you see? Maybe it's much better performance. I don't know, in fact. So if you want to increase this one more time, you can just fine tune it. Maybe it's 7. No, now it's a diverge, correct? Now it diverge. So, which means now we are oscillating, correct? Correct. We are oscillating. So we need to. So this one is too much. It's too much. So we need to reduce it. So now we are okay. We have good results here, right? So when you increase the learning rate a lot, we will have this situation here. We will just go here in the slides. We will have this situation. This one, do you see this one? Oscillating. So when the learning rate is too large, the gradient descent can overshoot. It will overshoot the minimum, and it may fail to converge or even diverge. Right? So we will have this situation. When it's very small, it will take more number of epochs. It will be slower. So if we reduce this one, for example, maybe it's very, very small value, we'll see. Look, it's very slow. In this case, we need lots of maybe 500 epoch. It's still also very bad, right? Maybe 5,000, right? 5,000. Now, do you see? No, so we can reach the same. We can reach the same result after 5,000 epoch because we reduced the learning rate, right? We reduced the learning rate. So maybe we need to add this one here, in fact, in the slide. So when it's eta learning rate, maybe when it's 0.001, okay. So it will take this big number. Sorry. Oh my God, what happened? So it will take 5,000 to reach the same results. So just for you. So do you see? It takes 5,000 epoch, and if we will increase this one, maybe we can just make it maybe 0.04. Of course, we can just say, okay, instead of 500, we will just select 50. Right, so we can increase this one a little bit also. We can just make it 0.6. So we almost have the same result in maybe 50. So do you have any question for this problem? Any question? Any question for that part? I mean, this part here, it's just it's a regression. I mean, we did regression. I mean, Rasmus, he did this regression last time, and from this regression, we got these results last time, right? So we have those regression results last time, and it's just the same. I mean, no difference. But it's linear regression, so maybe the I didn't make any comparison. In fact, I didn't make any comparisons between regression model and linear adaptive linear unit. Any questions? Do you have any questions? Sorry. Yes. Yes, Muhammad, he has a question in the code. Maybe we can discuss it after, after 12. It's about the dimension. So I don't know, maybe it's in how you define how you upload your data points. But you just revise the code and see if you can fix your problem. Okay, so he has been solving it. It's solved. Great. Okay, so any questions for that part? Do you have any comment about how can we use linear adaptive, this adaptive linear unit for regression? So we can use this linear adaptive linear unit for regression, for classification. This time we used it for regression. And then when it's a regression, just to remove that part. No need for threshold function. Do you remember? So we were returning it instead of returning the threshold function. So we have just deleted this function. Do you remember? We just deleted that part. Oh my God. Okay, so we just deleted that part. Do you remember? We just deleted that part. So this one, it's the threshold function. We used this threshold function last time. We don't need it here because our problem now, it's a regression problem and it's not classification problem. And if you want to make comparison, you need to make comparisons correctly. So we need to find prediction accuracy, for example, prediction error, and try to make good comparisons between regression and. So, for example, if you are working in a project, you need to do it correctly, right? So you need to do it correctly. And the impact of the learning rate when small learning rate, it's a slow converge, right? So we can just say here, it takes time to converge, but when it will converge faster, but it maybe also fail to converge. Maybe it will diverge. So we need to be careful. So this learning rate, it's a hyperparameter. The learning rate, it's a hyperparameter, and selecting this hyperparameter, you need to be careful also. But it's important to standardize your data set to be not very sensitive to this. The gradient descent will perform much better, in fact. Okay, so now we can go back to our slide. We just added one more slide here. So we added this one here to see the impact of your, and those are the parameters those are the model parameters. So omega and bias, it's the parameters of the adaptive linear unit, and those are M and C of the regression model. Okay, so now we need to activation function. Last time we had this question. We need to explore what type of activation functions we have, because those activation functions, they have huge impact, in fact. I mean, as you can see here in this adaptive linear unit, if we change from hard limb activation function into linear activation function, we can just, I mean, the function will be different. I mean, it can do different tasks. It can classify and it can be used for regression. So the activation function can be basically divided into two types: linear activation function and non-linear activation functions. We have this unit step activation function. I want you, in fact, I have also, I want you to implement it and implement its derivative. So this is the linear activation function. It's binary activation function or unit step activation function. Sometimes they call it hard limb or symmetric hard limb activation function. So in fact, it's hard limb or symmetric hard limb. It's hard limb or symmetric hard limb activation function. It's used for binary classification, and the derivative of the step is delta, which is the impulse function. Do you know the impulse function? So this is the impulse function. So in fact, it's 0 everywhere, and it's just 1 at this exchange from -1 or from 0 to 1. So this is the first derivative of this function. So we have this one, it's called binary function or hard limb function, and its first derivative is impulse function. And of course, this one we cannot use it for, I mean, gradient descent, because it will be just only 1 here. So it will not help us, in fact, to propagate error backwards. We cannot use here gradient descent, because in gradient descent we need the gradient, and it's non-convex. It's not convex function, so it's a problem, in fact. So we use it for classification. We use it for a perceptron learning rule. So this function, it's very simple. I mean, the output will be 1 when x or t greater than or equal 0, and it will be 0 otherwise. It could be 1, 0, and it could be 1 minus 1. So it's a 0, 1 when it's hard limb, and this one, it's symmetric, in fact. And it will be 1 minus 1 when it's symmetric hard limb. And its first derivative, it will be delta function, and the delta function, it will be like this blue one, right? So it will be 0 everywhere except at 0. At 0, it will be 1 or 2. It will be 1 in case of hard limb, and it will be 2 when it's symmetric hard limb, right? Sigmoid function. The sigmoid function. Sigmoid function. It is used as a squashing function. So it's the red one here. This one. So this is a sigmoid function, and mathematically it's exponential of x divided by exponential of x plus 1, or if you can multiply by exponential minus x. So this one will be 1 divided by 1 plus exponential minus x. So usually people use this form for describing sigmoid function, and it predicts probability of a binary classification problem. So for example, in our iris dataset, we have 2 classes. So instead of doing it like +1 and the -1, we can get the probability that this data point belongs to this class. So it could be 90%, it could be 80%, 50%, and so on, right? So instead of predicting the probability that this example belongs to this class or this class, instead of using hard limb function, we can use this probability function or sigmoid. And the first derivative of the sigmoid, it will be this one. It will be sigmoid multiplied by 1 minus sigmoid. So this is a sigmoid function. In fact, you can call it sig, right? I don't know, sigmoid, for example, and you can just call this one here sig minus sig times 1 minus sig. This one very important, because maybe we will use it with, maybe we can use it for, error backpropagation. So if you use this one in error backpropagation, this one will be very good. So the red line, it's the function, and the green one, it's first derivative. So the red one, in fact, it squashes all inputs, all positive inputs into one. Do you see? So I mean, we have here x greater than or equal 0, for example, or threshold. So all those positive values will be converted into a number between 0 and 1. Correct? So it squashes all inputs into a range between 0 and 1. Right? All negative values will be converted into 0. So this function is very important. I mean that is why when we mentioned the standardization, right? When you standardize, we are sure that all values will be located between, I mean, when the mean is 0 and the standard deviation is 1, we are sure that lots of variations of my data will be here, will be located here. But if you didn't standardize your data set, what will happen? For example, for this years of experience, we can take it, this prediction of years of experience. You will have very bad performance if you didn't standardize your data set, because years of experience, maybe it's from 0 to 10, right? So so most of the data are located here. Do you see? Maybe many years of most of the data are located above 5 or above 6 or 7. All those values will be converted into 0. So in fact, we lose information because I convert all data points. Most of the information which are stored in this feature vector or feature input will be squashed into 0. So I'm losing information. We will keep only those years, maybe between 0 and 2.5, 2.3 something. So we will keep variations here, but all data points above maybe 2.3 or 3, for example, it will be squashed into 0. So in fact, we lose lots of information, right? We will lose lots of information. So it's very, very important to standardize your data set in gradient descent because of the activation function, in fact. Because the kind of activation function which we are using, it will squash. Maybe you cannot see it in this problem here because we used linear activation function, but if you will use sigmoid activation function, we will have this problem. We will squash lots of variations into maybe +1 and the -1 or +1 and the 0. So it's very, very important to standardize your data set to avoid this this problem. So the performance will be much better because we will keep lots of variation of my data sets, my feature vector. So the green line, it's the first derivative, and if you can see, if the function itself squashes all inputs between 0 and 1, it's the first derivative. It will squash all inputs between maybe 0 and 0.3, 0.22, for example, right? Which is a problem, in fact, because when in gradient descent, in error back propagation, we propagate error backward. So in fact, this is the this is a gradient, right? So this is a gradient, and if we have multi-layer neural network, maybe we will multiply this value several times, and multiplying the small values several times will generate much smaller values. So at some point, the gradient will be 0, and we will not be able to update the weights of the first layers, maybe the input layer and the second layer and so on. The gradient will be very, very small, and we will not be able to update weights. And some of those weights will stay. I mean, when we initialize it with random values at the beginning, maybe we will keep those random values all time because we will not change it that much because of the vanishing gradient. So we have something called the vanishing gradient, because if you will use this sigmoid function as a cost function, as activation function, and you differentiate it, so we will get this one, how the gradient will look like, right? And if you will propagate through multiple layers, we will have multiplications of more number of gradients. And if the gradient is below 1, so this number will get decreased and decreased all time. And at some point, this value maybe will be very close to 0. And then when it's very close to 0, it means delta omega equals 0. And at some point, we will not be able to update our weights. This problem, we call it vanishing gradient problem. And to solve this vanishing gradient problem, in fact, you need to use different activation function which has better performance in the gradient, in the first derivative. So we cannot use sigmoid. We need to find some, we cannot use hyperbolic tan function. So in this case, we need to use other functions similar to ReLU, for example. We have something called softmax, and the softmax, it's known as normalized exponential function. It's normalized, it's exponential of x divided by the summation of exponential of x, right? We call it softmax or normalized exponential function, and it calculates the probability distribution of the event over any different events. So I have two classes, for example. So in this case, it will be exponential x1 divided by the summation of exponential x1 and x2. Exponential x1 plus exponential x2. So it's normalized exponential function. This one is very useful, in fact. So if we will use the softmax problem with the iris data set, for example, where we have 3 classes, so it will be, we will calculate this one 3 times. We will have exponential x1 divided by exponential x1 plus exponential x2 plus exponential x3, the summation of all events. The other output will be exponential x2 divided by the summation. The third one will be exponential x3 divided by the summation of all exponentials. So at the end, we will have normalized exponential function. It calculates the probability distribution of the event, and the summation will, the range will be between 0 and 1, and the sum of all probabilities will be equal to 1. So for example, the output in case of iris data set, maybe one output will be 0.6, maybe the other one will be 0.2, 0.3, and the other one will be 0.1, right? So the summation must be 1, must be equal to 1. The softmax function used for multi-classification model, and it returns the probabilities of each class, and the target class will have the high probability. So the one with the highest probability will be the target class. So softmax is multivariable function. Generally, you cannot take a softmax of a single variable. We cannot have a single variable. We cannot find softmax of a single variable. Just take a maximum of a single variable. I mean, for example, when we have only one output, we cannot use softmax. So, but when we have feed-forward neural network with 2 outputs, so in this case, we can use, it will be like this one, right? So at least we need to have 2 outputs. So I mean, the probability of the first output, it will be exponential x1 divided by summation of, or just exponential x1 plus exponential x2. The other one, it will be exponential x2 divided by exponential x1 plus exponential x2. So it's normalized exponential function, right? So if the first one is 0.7, the other one will be 0.3, correct? So this is example. I have some events. I have some x values, for example, and I try to calculate the normalized exponential function of the inputs. So it will be exponential of x divided by the summation of exponential of other x values. So if x is equal, I have 4 events, 2, 3, 5, and 6. So we will get softmax of x. It will be those numbers, and the summation of those numbers will be 1. Only yes, but you are right, Rasmus. But does it have any meaning? So it will be just exponential. Yeah, of course, it will be 1, correct? Because exponential x divided by exponential x, it will be 1. Yeah, correct. So it will be 1 all time. We will have 100% all time. Yes. So so hyperbolic tangent tan-h, its the range of the tan-h function is between -1 and 1. So sigmoid, the range of the sigmoid, it's between 0 and 1. The hyperbolic tangent, it will be between -1 and 1, right? So this is the function, and this is the first derivative of the function. The first derivative is very important, because if you need to write gradient descent, we need to find partial, I mean, we need to find partial E by partial omega, correct? So delta omega all time equal minus eta multiplied by partial E by partial omega. So it's very, very important to be able to find the first derivative of this function. Partial E by partial omega. We have partial J by partial omega. We have J, it's a cost function, but it's a function of t minus y, correct? So we need to find partial y equal 10hx, the input. So it's very, very important to be able to differentiate this function. So if you cannot differentiate it, we cannot use gradient descent here, right? So the red one here, it's the hyperbolic tangent, and the green one, it's first derivative. And if you can see also the first derivative, it's much better. Maybe it's much better than, maybe this one, it's much better than, maybe than sigmoid, because here, I mean, the maximum value here for the first derivative, it's maybe 0.22. But here for hyperbolic tangent, maybe it's 1, you see? So, I mean, this one would be much better for vanishing gradient, in fact. So it's exponential x minus exponential minus x divided by the summation of exponential x plus exponential minus x. Yes, and this is how can we implement it. I will show you the code, which I did last night. Okay, so this one, it's rectified linear unit. I want you to go through those activation functions. So rectified linear unit, it's the most used activation function in the world right now, in fact. And it's used in almost all convolutional neural network and deep learning. So this rectified, because we have this vanishing gradient problem. Do you know the problem? In shallow learning, we have multi-layer neural network, correct? So maybe you have 2 layers, 3 layers. It's okay to use gradient descent to adjust, to update the weights of 2 layers, for example. But when it's too much, when it's too deep, what will happen? We will have this vanishing gradient problem, and the gradient will vanish quickly. And at some point, we will not be able to update the weights of some of the layers. So we will just initialize it at the beginning, and maybe we will keep those random values with us all time, which will make a problem because of the vanishing gradient problem. So vanishing gradient problem, in fact, it was a problem when you try to make your feed-forward neural network too deep. Too deep, it means maybe if you selected maybe 5, 6 hidden layers. When it's 5, 6 hidden layers, the vanishing gradient problem will impact us, in fact, and at some point we will not be able to adjust the weights. You can try it, in fact. So you can try it. So I mean, try to use, for example, feed-forward neural network with iris, for example, and select, for example, sigmoid as an activation function, and try to see, try to propagate the error backward and try to check the value of the gradient. At some point, those gradients will be almost 0, and it will not help you, in fact, to adjust the weights. So it was a problem when we try to go deeply into a feed-forward. When we try to go deep in a feed-forward neural network and increase the number of hidden layers, we will have the problem of the vanishing gradient. And the vanishing gradient means the value of the gradient will be very close to 0. And then when it's close to 0, delta omega will be 0. And then when delta omega it will be 0, you will not be able to update your weights. So you will initialize it by some random values, but you will not be able to update the weights because of the vanishing gradient problem. So in this case, we cannot use sigmoid, we cannot use hyperbolic tangent. We need to find different functions which will not will help us to help us to fix this negative impact of vanishing gradient. So in this case, we can use, for example, rectified linear unit. So in this rectified linear unit, it has a range from 0 to infinity, in fact, right? So if you can see here, all negative values will be squashed into 0, this linear function. So the blue one, in fact. So in fact, the rectified linear unit, it's maximum between 0 and x. So all negative values will be squashed into 0. All negative values will be squashed into 0. And all positive values will remain the same. So if you have x, I mean, if we are talking about the income problem. I mean, this annual income. If your income is 10 million per year, it will remain 10 million per year. So we're not squashing it into one, correct? If you are using this function here, and if you are getting 10 million per year, for example, so it will be squashed into one. And if someone else who is getting 20,000 per year, it will be also squashed into one. So do you see? So we are losing very, very important information. We are losing, I mean, information about customers. You have customers, you build a model to predict something for a bank, for example, and we should be able to differentiate between the one who is getting 10 million per year and the one who is getting 20,000 per year. Now there is no difference, right? So now there is no difference because it has been squashed into this function. Moreover, also when we differentiate it, it will be, I mean, in maybe in this hyperbolic tangent, it's much better because I mean, it's numbers between 0 and 1. But in case of sigmoid, it's a problem really. In case of sigmoid, the first derivative, it will be number between 0 and maybe 0.22 or 23. So it's a very, very small value. And then when we try to propagate backward from one layer to another layer, we multiply several values from those small values. So it will be much, much smaller. At some point, this value will be 0, and it will not help us to train our model. So we can fix this one by, we can fix this value, I mean this phenomena, by using rectified linear unit. And rectified linear unit, it has a range between 0 and infinity. As you can see here, it's between 0 and infinity, right? 0 and infinity. And the ReLU activation function turns the negative input values into 0. It squashes all negative values into 0. So it's not mapping, in fact, the negative values, and it's disadvantage as well. So it's not mapping all those negative values. All negative values will be squashed into 0. And we can, in fact, we can approximate it using a soft plus. So soft plus, it's a smooth approximation to the rectifier. So instead of working with this one, because when we differentiate it, we will have little problem here. Instead, we can just use a softmax function. So the soft plus activation function will just approximate this rectified linear unit. So this is the rectified linear unit, and this is a soft plus function. So in fact, it's log 1 plus exponential kx divided by k. And this is its first derivative. So in the next slide, I made a code for plotting rectified linear unit. So we have this rectified linear unit. Do you see this red dot line? This is the rectified linear unit, and its first derivative. I mean, the first derivative of this one. This is ReLU. So ReLU, in fact, it's maximum between 0 and input x. So if the input is x, the output will be maximum between 0 and x, which means it will squash all negative values into 0, and the positive values will remain as it is. The first derivative of it, it will be just, you know, this one, this red one here, when it's 0, it's 0. So the first derivative of 0, it will be 0, and the first derivative of x, it will be 1, correct? So in fact, it will be a step function. So the first derivative of rectified linear unit, it will be a step function, which will be much, much better, in fact, than for example, sigmoid. So the first derivative of the rectified linear unit, it will be values between 0 and 1, correct? So it will be this step function. If you want to use the soft plus as an approximation of the ReLU, this one will be the soft plus. So this is the soft plus. It's log 1 plus exponential x. Okay, it's len 1 plus exponential x, this one, right? So we will just implement it as it is. So it's log 1 plus exponential x. So this is a soft plus, the red one here. So the soft plus, in fact, it's approximation of ReLU. And the first derivative of it, because this one, it's log 1 plus exponential. So the first derivative of it, it will be sigmoid, correct? So the first derivative of the soft plus will be a sigmoid. So in this case, I mean, the range will be numbers between 0 and 1. it will be much better compared to the sigmoid, because when we go to the sigmoid, we can see that the first derivative will be numbers between 0 and 0.22 or 0.24, right? So several multiplications from this one, we will get very small numbers here. So in this case, the gradient will be almost 0. When we go deeply, maybe it's okay for the first layer, first hidden layer, but if you have 2 hidden layers, it will be really a problem. Yes. So we have those, you have all those functions. Maybe if you can go to, I will try to find this function and add a link to it. Okay, file, open notebook. It's called the activation, in fact. It's called the activation functions. Yes, this one. So I have this file. It's called activation_functions, where I implemented all activation function. You can add more, in fact. So I just added some, but if you want to add more, you can just add more. I mean, the activation function, it's based on the knowledge, in fact. Yes, of course, you don't need, yes, really, you don't need, correct, Muhammad? So Muhammad, he has a question. He said that, so we don't need to standardize the data in RELU. This is one advantage in deep learning, in fact. In deep learning, usually you are working with raw data, right? So if you are using RELU, maybe you don't need to standardize your data set. Because in deep learning, we are working with raw data. In deep learning, we are working with raw data, so there is no big need, in fact. But if you can spend some time and try to fix your data point, I mean, if you can standardize your data, if it will be a habit for you, maybe it will converge faster, right? You don't need literally to do it, in fact, but if you can do it, so if you, I mean, we have a pipeline. If you can just follow the pipeline, it will make life much easier. But deep learning, in fact, it's meant for working with raw data. We can just work with raw data. So if you will use RELU, maybe you don't need to standardize your data sets, right? And you can just work with the raw data. You are correct. Yes. So you have this activation function. You can just run it. It will be used just to plot each activation function, right? And its derivative, right? So I did it for step function. I did it here for step or hard limb. It's hard limb, or you can just call it hard limb or symmetric hard limb. So just in this case, it's a symmetric hard limb. Sigmoid activation function. We have the function and we have its first derivative, right? It's very important to plot its first derivative to understand its impact in the gradient vanishing gradient problem. This one, it's normalized exponential. We cannot plot it, of course, right? So normalized exponential, we cannot plot it. But we did it for some events. I have 4 inputs, and we can plot, we can get the summation, we can get the probability that each one belongs to this class. So we'll have it like this one. Hyperbolic tangent. This is the hyperbolic tangent. This is the function, and this is its derivative. If you compare this one with sigmoid, this one much better in terms of vanishing gradient problem. So this one should perform much better than this one. Rectified linear unit. We used here rectified linear unit and soft plus. So we have rectified linear unit and its first derivative, and also we have soft plus. Soft plus, it's an approximation of the rectified linear unit. To avoid this, I mean, step function, I mean, abrupt change, because it was 0, suddenly it becomes 1. So to avoid this problem, you can just use soft plus function as an approximation of the RELU. And there are many other functions. So there are many other functions. So there are many other functions. There is something called the parametric rectified linear unit. Parametric rectified linear unit. Because as I told you, in the rectified linear unit, we have a problem of squashing all negative values into 0. So to avoid this problem, because now we are losing information. So imagine you are collecting data, and in those data, you have some negative values, some positive values. So if you will use rectified linear unit, what will happen? We will squash all negative values into zeros. So we are losing information, we are losing knowledge. So in this case, you can just go for parametric rectified linear unit. You can go for exponential linear unit and soft plus. I mean, we implemented anyway soft plus. So in fact, I suggest that you can go for other functions here and try to, for example, linear function, binary step, we did it. Logistic regression, we soft. I mean, it's a sigmoid, right? 1 divided by 1 pi plus exponential minus x. Tan hx, it's a hyperbolic tangent. Arc tan, maybe you can do it, right? We didn't do it. So this parametric rectified linear unit, you need to do it. So you have the function and you have its first derivative. You have the function and you have its first derivative. And when you are solving a problem, when you are working with a problem, I mean, there is no rule. It's maybe but trial and error. You need to look into your data to decide which function we need to use. So you need to get some domain knowledge, in fact. And if you don't have this domain knowledge, because you are engineer and you are working with data science, so just need to visualize your data set to get some understanding of which model should we use, which activation function should we use. So I propose that you can go to this table, for example, and try to implement the rest of 2 functions here in this one. So we can have all functions. We can have all functions plotted and its first derivative, so we can get better understanding, because it will help us a lot to see if for example, if someone asked you what is the difference between parametric rectified linear unit and rectified linear unit. So in this case, you need to plot the function and its derivative, in fact, right? So we need to do it to understand what is the difference. So it will be really very useful. Why differentiation? Because we have been talking about differentiation because of gradient descent. Differentiation is important because of the gradient descent. So the main use for differentiation here is to find the gradient of a function at any point on the graph. We need to find the gradient of the function. What function? It's the cost function. So we need to find the gradient of the cost function, because the gradient of the cost function is the one which we use for updating our weights. So imagine that you have you have this function. It's a very simple function. It's y equal x squared minus 2x minus 3. And we need to find the minimum. We need to minimize this function. We need to find the value of x, we call it x star, which will minimize y, right? How can we do it using a gradient descent? We need to find the first derivative of this function. So we need to find the dy by dx. This one will be the gradient. It will be 2x minus 2. And we need to start at some point here in the graph by random. We just select any point. Imagine here, we are here. So at x minus 1, for example, we are here at some point here. We selected by random because we need to solve the problem in steps. So we select by random x equal minus 1, right? Because I'm selecting. So my algorithm selected x equal minus 1. So at that point, I need to evaluate the gradient. So dy by dx at minus 1, it will be minus 4. So in fact, the slope here will be minus 4, right? So it will look like this one. So the slope of the line of the tangent, it will be minus 4. If you want to plot it, how can we plot it? Now I have the slope of the line, dy by dx, it's the slope. So the slope, it's minus 4. If you want to plot the tangent, I want to find its intersect with y. So how can we find it? Just substitute this minus y here into this equation if you want to find y. So y will be minus 1 squared, minus 2 times minus 1, minus 3. So it will be 0. Is it correct? No, it will not be 0. It will be, this one, it will be 1. Yes, it will be 0. So now, okay, so y here, it will be 0, right? So now I want to find the equation of this line. So I can use this equation y minus, yes, correct, because at -1, what is the intersect with y, in fact? So I have here x equal -1. When x -1, I find the slope at that point, right? We can find the slope, but I want to find the intercept with y, or I mean, there are many ways. So it could be y equal mx plus c, for example, and we can use this equation of the tangent y minus y1 equal m slope multiplied by x minus x1. So x1 it will be -1, and y1 it will be 0, correct? And the slope will be -4. So finally, the equation of the tangent will be -4x minus 4. -4x minus 4. So this is the equation of the tangent. So anyway, we need the first derivative because we are using a gradient descent, and to update. So if I want to find the delta x here, so delta x will be minus learning rate minus eta multiplied by delta y by delta x. Correct? So if I want to solve this problem, so I can write this equation here. So we try to solve this problem, right? So we need to find delta. We need to find the delta x, correct? So delta x will be negative learning rate multiplied by delta y by delta x, dy by dx. So it will be, if we can go to the equation, what is dy by dx? It's 2x minus 2, right? So it will be x minus 2, right? So it will be like this one. This is a step which so if you selected here x equal -1, what will be the next step? So just select eta equal 1, right? And dy by dx equal dy by dx, it's -4, right? So this one will be 4 eta. So this one will be 4 multiplied by the learning rate, right? So it will be like this one. So this is the delta x. This is the step which we will use, in fact. And if you want to update x, so x equal x plus delta x, which equal x plus 4 eta, this one. So I will just explain it to you. So now let us do it. So now we find the slope of the line, which is -4. So I find the delta y by delta x, and I find this value equal -4. I will substitute this value here, so it will be 4 multiplied by the learning rate. The learning rate will help me to find the step which we need to use. I need to reach this point here, right? So I am at -1. Imagine that we use the delta equal maybe this learning rate equal 0.1, right? So if it is 0.1, what will happen? So x will be -1, right? -1 plus 4 times 0.1, if it is 0.1. So finally, this one will be minus 4.6, correct? So this is the gradient descent. So it's important. So this is an example, correct? So I started by random at -1. So the next step we are reaching or going here closer to the because the minimum here may be at 2 or something, right? In fact, at 1. should be at 1, right? So now we are at minus 0.6. And if you increase the learning rate, if it is 0.2, so this one will be minus 0.2. If you increase it minus 0.3, for example, so it will be plus point value here. So we will jump from here to a point closer to the minimum using this formula. Is it okay? So differentiation is very important for gradient descent. Okay, because we are so this is the derivative of the activation functions, different activation functions. And if you look into the green one here, it's for sigmoid. So the green one here, it's for sigmoid, and it's very bad. It has very bad performance with vanishing gradient. And this is RELU. This one, it's RELU. Right? This one, it's RELU. And this one, it's for soft plus. This one, it's for soft plus. So the derivative of the activation function is very important for gradient descent. And it's just a graph for RELU and the vanishing gradient, right? So if you will use sigmoid, so just comparison between sigmoid and RELU, right? So you have sigmoid. So this is a sigmoid function. This is the first derivative of the sigmoid function. And this red one, it says RELU. And this is, it's a soft plus. I'm using soft plus as an approximation of RELU. So in fact, do you see? So the first derivative of the soft plus, it will be sigmoid. So we are using a sigmoid as gradient for calculating the gradient. So the performance will be much better. Because if I'm multiplying, if I'm doing those, because in deep learning, we have lots of multiplications. If you have 20 layers, for example, if you have 50 layers, so just imagine multiplying 1 by 1 by 1 by 1, you will get 1. 0.9 by 0.95, so you will get large values. So the performance of the soft plus or the RELU is much better in case of vanishing gradient compared with sigmoid. So, and you have the code. You have the code in GitHub also. You can just go for it, and please, you can complete it. In fact, just complete it. Add other functions. We have in the table here many functions. So try to add more functions to this example in GitHub. And or you can just make it and send it to me so I can add it to the file. So we can have all functions implemented. Yeah. Okay. So vanishing gradient problem. It's we have this problem when training artificial neural network with gradient-based learning methods. We have this problem in gradient-based learning methods and the backpropagation. And it describes a situation where a deep multi-layer feed-forward neural network or recurrent neural network is unable to propagate useful gradient information from the output end of the model to the layers near to the input. And hence, the inability of the model with many layers to learn on a given data set or prematurely converge to a poor solution. So this gradient, vanishing gradient, it's a very dangerous problem, in fact, very dangerous. And it ends up with a model which is prematurely converged to a poor solution, or a model which is unable totally to learn my data set. So in gradient-based learning, each of the neural network weights receives an updates proportional to the partial derivative of the error function. We have partial E by partial omega. So in fact, the updates is proportional to the first derivative of the error function with respect to the current weight in each iteration or training. So we have this problem. If partial E by partial omega will be very, very small, but also imagine that we have this partial E by partial omega. It's a chain rule. We have chain rule. So we find partial E by partial Y multiplied by partial Y by partial net multiplied by partial net by partial omega. So we have lots of multiplications. So of those, and we will repeat this one several times, one time for each layer. So imagine we have deep neural network, and we have many hidden layers. So it will end up with very, very small delta W values. And maybe those delta omega values will be very close to 0. And in this case, when it's almost close to 0, we will not be able to adjust the weights using this formula. And it ends up with a model which is premature, or a model which is unable, in fact, totally to learn and to fit my data set. So this is very, very important problem. So vanishing gradient problem, I mean, in some cases, the gradient will be vanishing small, effectively preventing the weights from changing its value. And in the worst case, this may completely stop the neural network from further training. It will stop some layers, at least some layers. So we will stop some layers from training, and we will keep the random initial values which we used from the beginning. So as one example of the problem cause, traditional activation functions such as hyperbolic tangent function have gradient between 0 and 1. This one has gradient between 0 and 1. And if you will go to sigmoid, it will take values between 0 and maybe 0.2, for example. So this has the effect of multiplying n of these small numbers to compute gradient of the front layers in an n-layer network, meaning that the gradient or the error signal decreases exponentially with n, while the front layers train very slowly or not train at all. So it will be a problem. So how can we solve this problem? By using different activation functions. Yes. So finally today, I want to talk about the training mode or the learning modes. So we have 3 learning modes. We have mini batch, we have batch gradient. Okay, so we have batch gradient descent, and we have stochastic gradient descent, and we have mini batch gradient descent. In batch gradient, we minimize the cost function by taking a step in the opposite direction of the cost gradient from the whole training set. In each epoch, we do it one time for each epoch. So we minimize the cost function by taking a step function in the opposite direction of the cost gradient from the whole training data set. We call it epoch. And it's very computationally expensive, especially for large data sets with millions of data points, where we need to re-evaluate the whole training data set each time we take one step toward the global minimum. So this is a problem. It's computationally expensive. So the batch gradient, and also it requires memory because we need to keep all data points in the memory. So the batch gradient descent, we update the weights using the cost gradient from the whole training set. So we calculate the cost gradient or minimum or mean gradient, for example, from the whole data set, and we use it for adjusting the weights of the neural network one time each epoch. This one, it's a problem because we need to keep all data points in the memory because we will do those calculations we will make those calculations each epoch. So we need to have really a good computer with a good memory, and it's computationally expensive also because we will do this for all data sets. We will calculate the gradient for all data set, and we will use the cost gradient one time from the whole training data set for adjusting the weights. It has advantage and a disadvantage. Advantage, it's disadvantage first, it's slow, it takes time, and we need much bigger memory. It's computationally expensive because we need to do those calculations each epoch for the whole data set, right? And it takes many epochs to converge. So it takes more time, in fact, to converge. Advantage, we will have smooth converge. We will converge smoothly because we use, in fact, the mean value of the gradient. So we use the mean value of the gradient from the whole data set and use it for adjusting the weights. So the curve will be very smooth. It will not bumpy curve. It will not be noisy curve, but it will be very smooth curve. And this smooth curve, in fact, it's good because maybe it has high momentum, maybe. So sometimes it will help us to escape from maybe some of the global minimum, local minimum, maybe. Stochastic gradient descent, it's called iterative or online gradient descent, iterative or online. Why it's online? because instead of updating the weights based on the sum of the accumulated errors, I mean, in batch gradient, we use accumulated errors. But here, we will do it example by example. So instead of using the accumulated sum of errors over all samples, we update the weights incrementally for each training sample. We do it sample by sample, example by example. It converges much faster than batch gradient because we have more frequent updates. So it converges much faster. So maybe in few epochs it will converge, right? But in batch gradient descent, it really takes more number of epochs. But this one, it can converge faster because of the more frequent updates. We update much faster. The gradient is based on a single training example. We do it example by example. So the gradient is based on a single training example, and therefore the error surface is noisier and it can escape shallow local minima. So I mean that the error surface will be bumpy or noisy, in fact. And when it's bumpy or noisy, maybe it will be useful for escaping from some of the local minima. And to obtain satisfying results using stochastic gradient descent, it's important to shuffle the training set for each epoch to prevent cycles, right? So in fact, we need to shuffle, and maybe each time we need to shuffle. So in each epoch, we need to reshuffle, right? But in case of batch gradient, we don't care. In fact, we don't need to shuffle because we use the accumulated error over the whole samples or the whole data set. So here, in fact, we don't need to shuffle at all because we calculate this accumulated errors over the whole data set. So it doesn't matter for us, in fact. But in case of stochastic gradient descent, we need to shuffle each time. In SGD, learning rate is often replaced by an adaptive learning rate. I mean, we can just use an adaptive learning rate, which may be C1 divided by number of iterations plus C2 or any other formula. So it's constant number divided by the number of iterations plus another constant number, right? And C1 and the C2, of course, it will be hyperparameters. It can be used for online learning where our model is trained on the fly as new training data arrives. In case of stochastic gradient descent, we don't need, in fact, to store any data points, right? So when we are getting a data set, we can just use it for tuning or fine tuning or training the model, and just forget about it, right? So we call it online learning. So in case of online learning, we just adjust the weights one time for each new example. I had, I mean, the exam last year, for example, it was written. I mean, this year it will be oral exam, but the last year, for example, I give students a question about number of learnable parameters. How many parameters in the model, for example, and also how many updates in case of batch gradient descent and stochastic gradient descent, and the mini batch gradient descent. So you can calculate how many updates we will do, right? So for example, if you have a model and this model has 100 parameters, for example, and we will train the model for 100 epoch. So how many updates? It will be 100 times 100. In case of stochastic gradient descent, you have a model and we have 100 data points, right? Here, we don't care about the number of data points because we will do those updates for the whole data set. So we don't care here about the size of the data points. But in case of stochastic gradient descent, it's very important to know the size of the data set. So if you have a data set consists of 100 examples, you have 100 parameters, and you will do it for 5 epoch. So how many updates, right? So the number of updates will be number of epochs multiplied by the size of the data set, and number of examples multiplied by the number of parameters. So this is the formula, how the formula will look like. And the mini batch, it's a trade-off between the two examples, between the two modes of learning. Because we have a problem here, right? So in batch gradient, for example, sometimes in batch gradient it's smooth and it's, I mean, but imagine you have a data set which consists of 10 million data points. Maybe your computer will not be able to handle it, right? So you want to go for batch gradient, but your data set is really very large. So I need to keep all those data points in my memory. My memory will not be enough. So in this case, I cannot go for batch gradient, and I can go for mini batch gradient. And in mini batch gradient, we will divide my data set into batches. Maybe the batch size will be 32 data points or 64, 512, for example. And this is the size which my memory can handle, right? So I will divide my data points into batches, and I will use, so we apply batch gradient descent to smaller subsets of the training data, for example, 32 samples. The advantage over batch gradient descent is that converge is reached faster by mini batches because of the more frequent we update. In this case, we will update more frequent, because if I have my data points and it consists, for example, of 100 data points, and I divided it into 5 batches, each batch is 20. So in this case, we will multiply the number of updates by 5 number of batches. So in this case, we will increase the number of updates. So the number of updates in mini batch learning, it's much more than in batch learning. So we should expect that the model can converge here, can reach conversions much faster than batch gradient learning approach. Yes. So now we need to go to the adaptive linear unit, and we need to apply. I mean, we used the batch gradient. In fact, I mean, the example which we did with iris dataset. In fact, it's batch gradient. It's batch gradient. So now we want to re-implement it using this stochastic gradient descent and the mini batch gradient descent, and make comparisons between, I mean, the solution. For example, we need to know which one will converge first, which one will have better performance, better accuracy, and so on. So we need to have this example. I mean, this adaptive linear unit, which we did for iris dataset. It was for batch gradient, in fact, batch gradient. So now we re-implement it using stochastic gradient descent and the mini batch gradient descent. And we need to make comparisons between number of epochs, time used for, I mean, enriching time, I mean, just actual running time, for example, memory use, and so on. So you need to make those comparisons. So please just go to this version 2. It's adaptive linear unit version 2 in GitHub, and try to run it and see. So I have this one. It's called adaptive linear unit version 2. So just open it, please, and let us try to. It's with iris dataset. In fact, I made some changes here. Okay, no, not this one. In fact, maybe by the way, I make mistakes and I store things with different names, and I feel that I made a problem, in fact, because version 2 I cannot find it here, right? Okay, so this is version 2. No, in fact, it's sad because I changed it. In fact, I changed it into. No, maybe. Okay. Okay. So no, it's another one. In fact, it's this one. Okay, it's adaptive linear unit BGD versus SGD. Yes, this one. So it's for iris dataset, and I added here if mode equal batch gradient descent or stochastic gradient descent. Mini batch also, you need to do it for mini batch. So in fact, you should do it also for mini batch. Thanks, Rasmus. Thank you very much. So please just go for this one and run it. So this is the old part, in fact, for BGD, and this is the new part for SGD, right? In batch gradient, we do those calculations for each epoch. I'm using the mean value here. Do you see? I'm using the mean gradient for the whole data set for updating my weights. But in case of SGD, we do it example by example. But I did it for only one. In fact, I did it here for only one. Okay. So this is the number of epochs. So we will run it for a number of epochs. And if the mode is BGD, you will do it here. And if the mode is SGD, you will do it example by example. So do you see this for loop? So we will calculate net for each example. We will calculate the error. So this error value here, it will be scalar value, but the error value here, it's a vector. And we will update weights. So instead of using the mean value, over the whole data set, we will just do it example by example. And this is comparison between results. So we have here, this is the training error in case of BGD, and this is the training error in case of SGD. You can see that this one is smooth, right? This one, it's noisy, error surface. So the error surface here, it's noise. This one, it's smooth. This one requires more epochs to reach convergence. It takes 10, for example, or maybe 20. But this one maybe 4. After 4 epoch, we can reach convergence. So the error value here, it's too much. It starts from very high value here. Do you see? But we are starting here from very, very small value. So this is a decision line in case of BGD, and this is a decision line in case of SGD. So just please make comparisons, but I can run the code with you from here, but you need to modify it, in fact. So you need to modify it, and you need to add mini batch gradient. So you need to modify it for mini batch gradient. So I will run that part. Okay, we're uploading our data. We just try to extract X and Y values. Prepare our data in the correct format. And this is our class. We are using here, I don't know, do we normalized feature scaling? So we have here standardization, feature scaling, or standardization of data. Okay, so we will train the model using SGD. So this one using stochastic gradient descent. Do you see? This is a stochastic gradient descent. And if you want to do it for BGD, just change this one into B. No, it does not converge because maybe the learning rate is high. We need to reduce it. So now we have good results. And of course, we started from high value, and it might need more epoch. So I just selected 100. So now it's okay. We plot this one. So this is the results of the BGD. Of course, it's very bad results, but we need, it's not good results because we have, the accuracy, we have some misclassified. I need to zoom it, in fact. But I don't know how can we zoom here. Is there any way to do it? Maybe this one is too much. Maybe just -1 +1. So do you see it's, I don't know why we have this kind of overlap. In fact, they are very close from each others. But I can maybe we can reduce this one more. But when we reduce more, we will need more epochs. Maybe it's too much. Maybe 20 is okay. But do you see the error is too much, in fact? So the error here is too much. Yes, it will be like this. I don't know if we can increase this one a little bit to see. No, it's much better, in fact, much better. So anyway, you need to revise this one. If you want to test it for stochastic gradient descent, yeah, it's yeah. So anyway, I mean, you just need to make comparisons. So maybe it could be like a small home assignment for next time. We need to make some comparisons. You need to try SGD, BGD, right? I mean, next time we should start working with. I had also another part today. If you, but anyway, I can give you, for example, 2-3 minutes to try this code, and if you have any questions. And maybe next time we can, I mean, I had a plan today to start working with some of the packages from Python, but we need to go also for feed-forward neural network and error back propagation. But please, you can just take 2-3 minutes with this code, try to run it on your computer, and let me know if you have any questions. So in comparison, because when you have two algorithms, when you are publishing any results, you need to make good comparison between those algorithms. You need to find, yes, here we have question from Michelle. Yes, yeah. Michelle. Mm-hmm.
My question is with the computational cost associated with the BDG and SDG. Mm-hmm. Looking at the code, with the SDG, you have to iterate through the entire length of your feature set.
Yes, correct. No, not the feature set. The feature sets we are using all time. So if I have 2 features, I must use those 2 features. You iterate across the data points. The example.
Yes, mm-hmm. Like the number of rows.
Yes.
But in the BDG, you don't iterate through. But I'm sure it is the same as the dot product of the error and then the.
Yes, you are correct. You are correct. In fact, when you go for batch gradient descent, we can use this. This one, it's vectorization. Do you know?
Yes.
So we can take advantage of vector. I hope if I'm correct. Is that correct?
Yes, it's the same. So the vectorization is just the same as the iteration. So is the additional computational cost the summation or the mean?
No, because if you need to, I need in each epoch, I need to calculate this one each time, right?
Yes.
For all data, this one we are doing it for all data points, correct? All X.
Yes.
So in fact, in the computational cost now, I need a computer which has a memory to carry all my data points X.
Okay.
But here in this example, do you see? Here in this example, we have only one line.
Oh, okay.
One row, correct?
Okay.
So my memory here, I just need a small memory to just imagine it's images or video or something.
Oh, okay. I understood. First, I thought it was from a purely computational cost, but from a memory side, it's understandable. But from a computational cost, it's almost the same.
Yes, it's for the memory. And also, if you imagine that you have images and you have deep learning, for example, and in this deep learning, you have maybe 50 hidden layers, and it will take really too much time for calculating one shot like this one. Now it's
Okay.
very simple here, but if it is in deep learning, for example, you have a multi-hidden neural network, for example, and its images and feature selection. I mean, it will be more complex. Now it's simple here in this example, but maybe in some other application it will be really very tough, right?
Okay, sure.
To go for this one shot and make those calculations each time, keep it in the memory, because I need to keep X in the memory. And after making those calculations, I need to keep this one in the memory, right?
Yes.
And after that, I need to calculate errors, and I need to keep it in the memory. I need to keep this one also in the memory.
Yeah.
Right?
Yes.
So I will keep this one in the memory. I will apply this activation function. I need to keep each time this one in the memory. I need to keep this one in the memory. Calculating the error, I need to keep it. Now, when we calculate this one, I don't need to keep this one anymore, right? So I can clean this one from the memory to make some space, update the weights, repeat this process in the next epoch.
Okay.
So we will repeat this one. So in fact, I need to keep this one. I need to keep my data points. And imagine if it's 1 million images. Are you able to do this?
No, it will be very difficult.
So if you are working in a medical image problem, for example, and you have, for example, a data set which consists of maybe 100,000 image, and the image has maybe 1,000 times 500 pixels, and it's 3 channels. So really you can calculate the memory use. It will be really very tough. And in calculation also, it will be, I mean, you will consume lots of energy, really. You will see your computer is just fighting to make those calculations. So at some point you will say, okay, no, I cannot do it using a batch gradient. I need to use mini batch gradient. And in this mini batch gradient, we will divide X. So if you have any memory issue using batch gradient, so I cannot deal with X in each time, so I can divide it into mini batches, right?
Yeah.
So if you want to implement a mini batch here, so I need to divide X maybe into some mini batches, maybe 2 sections, 3, 4, 5, 6, 10, correct? According to your computer. So if you will use a batch size equal 512 or 64, imagine that it would be 64. So in this case, I will deal with each time with a block of data equal 64 examples instead of working with the whole data set at once. So in the mini batch, in fact, it's like we try to fix this memory problem, and at the same time, when we make it mini batches, so I will update more frequent, because we have this. This one will be repeated for each mini batch. So if you divided your data point here into 5 batches, so in this case we will increase the number of updates by 5, multiply it by 5, right?
Yes.
So you should reach conversions much faster in case of mini batches, and your memory use will be more optimum. So you need to select what is the size of the mini batch. Also, it's hyperparameter, and it's based on the memory capacity which you have in your computer. So please, I mean, from today until we meet again next week, please try to implement mini batch gradient. Right? So I can just add here a comment. Implement mini patch. Okay, so this one, it's home assignment for next time. Is it okay? Michel?
Yes, I'm fine.
Yes.
Thanks.
Yes, please. I mean, try to implement this mini batch gradient descent in that part, and we can test it. I mean, our example, it's a simple example. So, I mean, there is no way, in fact, for us to test it, but at least computational time, you can just calculate the time here, which will be used in the training. So we have a function which measures the time for training. We can just calculate the time used for training and make some comparison. We will see some comparison, I'm sure. We will see some difference. So we need to compare between BGD, SGD, and the mini batch gradient descent. But you need to implement mini batch gradient descent here in that part.
Okay.
Mm-hmm. So just please, I mean, just to try to try to implement mini batch gradient descent and make good comparison between the 3 learning modes, because those 3 learning modes are very, very important to understand before we go to deep. I mean, in deep learning, we will not do much programming. In deep learning, they have all those functions already, and so the most effort, in fact, which we need to do, it's in this part here, in this shallow learning part, where we try to make something, implement those stuff to understand the concept behind it. But when we go for deep learning, and even in shallow learning also, we can use it as a black box, in fact. So we can just use it as a black box, but we need to understand in the first few weeks, we need to understand the concept behind each approach. And after that, life will be much, much easier, because we will deal with packages developed for Python, which makes those stuff are very easy. In fact, it will be just a very, very simple one. Yes, I guess it's 12 now, so we have 1 minute left. So please just let me know if you have any questions.
What were we supposed to compare between the different modes? Batch gradient descent and mini batch on those?
Yes, who is asking the question, please?
It's me, Rasmus.
Yes, Rasmus. Yeah. So Rasmus, we need to make comparison between. We should just select any data set. You can work with iris or you can work with images, right? So just select. You can go, for example, for MNIST data set, for example. It will be more heavy, for example, but it has 10 classes, so I don't know how you will do it. So we need to make comparison between batch gradient, mini batch gradient, stochastic gradient descent. Those comparisons, it could be in the maybe a prediction accuracy, it could be time, it could be memory, for example. So try to find. I just need this table and the code also. So if you will write the code for that part, it would be great if you can share it with me, so we can add it to this file in GitHub. So we need to have that part done. Yeah. Yes. Any other question? Any feedback for teaching? Do you want to change anything? Should we do things in different way? I mean, from last week, we have this slides of lecture 2. We didn't finish it. We didn't complete it, in fact. So maybe next week we will go back to it, and we will continue also with new parts, step by step. For the cost function, also here, it's hyperparameter, in fact. So which cost function you will use? It's hyperparameter, right? So I mean, here we use the mean squared error. So I have the error, we calculated the error, and I squared it, and after that I divided it by the number of examples, or so to get the mean error. So so just to try to implement this one and share it with me until we meet next week. Yes.
Professor, do we have an exercise lecture this Wednesday?
Exercise?
Lecture this Wednesday, because we have 2 scheduled lectures each week.
Yes. In fact, we should have 2 hours for lab work, but the one who should do it, in fact, he is not here. He has some family issue and he traveled. So maybe we don't need those 2 hours. When we need it, I will just mention this. So, but I guess you have all code now in GitHub. You just need to read the slides one more time, extend your reading, try to find other sources to, extend your knowledge, and try to use those Colab code for also maybe extending it for other examples, and try to work with, play with other data sets and other examples. So I guess we don't need those 2 hours in each Wednesday at the moment. And when we need it, I will just inform all of you. But also, if you need help, just tell me, and we can meet in those 2 hours and make some examples and small coding and stuff like this. But at the moment, I feel that we don't need those 2 hours. But if you feel that you need those 2 hours, just inform me, so we can at least meet in Zoom, for example, and I can see if you have some problems, if you are coding, if you have some. But we have some teaching assistant who should be running those 2 hours. but at the moment, I will fix it with him because he is not here at the moment. But I will try to fix this with him as soon as possible. Yeah.
Thank you very much.
Thank you very much. And please, if you have any question during the week, just send me an email, and I will try to answer you. Yes, for Abdurrahman, we have. Do you have access to Blackboard? Yes, if you have access to the correct Blackboard, we have all materials uploaded there. We have some folders. I can show you the Blackboard. So I will just open it and to show you.
Yeah, I have access to it and I can see all the materials.
You
but
cannot
the problem
see.
was I can see. I can see.
Okay, you can see it.
Yeah, the problem is today, at the beginning, I didn't know where to connect till I emailed you before you sent me the link.
Yes,
Maybe
because sorry, I didn't check also my email after I started. I saw your email at 10 almost. So,
yeah. But maybe you can add me to the mailing list so I
added you already. So
okay.
Next week you will get invitation for Zoom lecture, and
Okay.
also we are recording this
yeah.
lecture. So I will
Yeah.
share also the link with all people in Blackboard. So if you are missing some parts, you can go back to it. And also we have also recording from last week.
Okay.
So you can go to it also. And if you have any question in the week, we can meet here in the office, or we can you can just send me an email and we can discuss.
Okay. Yeah. Okay. We can meet in the office because I'm in Trondheim.
Oh, okay, it's fine.
Yeah.
just call me. Use Skype for business.
Okay.
Yeah, and we can discuss. If you have any questions, we can discuss anytime.
Okay. Yeah. Okay. Thanks a lot.
Thanks a lot, man. Thank you very much. Okay, guys. Any other questions, please? So we have here Blackboard. You can just go to Blackboard and you can find all materials. I try to upload my lecture before teaching, but for example, today we updated the slides, and the one in Blackboard, it's not the one which updated. So where is the course? Okay. So we have this one here. So you can go to this under listening material. You have those lectures, the data sets, code, video lectures. In this video one, we have recording from last week. So if you are missing something, we can just go to this one. Yeah. And I guess also maybe I uploaded it also to YouTube link, and I put it in the announcement. So we will do the same this week. So you will have all materials. You have recording. The code, we don't have any code here, in fact, because we have all code in GitHub. So it's more organized when it's in GitHub. So just upload it and play with it, and try to run it. And if you have any problem, just contact me. Lectures, also slides, it will be here. And also I'm uploading it also to GitHub. So we can have all materials in the same place. And also the data sets, which we have also, I uploaded it to GitHub. So we can have all materials in one place. Yes. Any other question? Any other questions for today? Okay, so the home assignment for next week, it's very simple this time. It's just to try to run the code in GitHub one more time for today, and try to run SGD and BGD and the mini batch gradient, and try to make comparisons between all those different modes of learning. Yes. And thank you for joining me today, and I'm looking forward to meet you again next week. Thank you very much. Bye-bye.